What if everything we know about reality is just a small part of something much bigger and more mysterious? The universe is vast, going beyond what we can even imagine. It has secrets ranging from how it began with a huge explosion to its complex structures and hidden forces like dark matter and dark energy. Join us as we explore the mysteries and everything we don't yet know about the universe. The Big Bang represents the moment when our universe began to expand from an infinitely hot and dense state, roughly 13.8 billion years ago. However, the precise cause of this monumental event remains one of the universe's most profound mysteries. The prevailing theories suggest that the universe went through a rapid expansion, often described as inflation, which occurred very shortly after the initial explosion. This inflationary phase helped shape the large-scale structure of the cosmos we observe today. Before the Big Bang, conventional understanding struggles to provide a clear picture. Time and space as we know them originated with the Big Bang itself, which complicates our ability to discuss before. Scientific theories propose that our universe may have existed in a different form, or even suggest the possibility of multiple, interconnected universes. Some hypotheses consider a state of quantum fluctuations in a vacuum, a realm where traditional physical laws break down, leading to the spontaneous emergence of our universe. Additionally, certain models suggest that our universe might be part of a cyclical process, going through phases of expansion and contraction, hinting that what came before could have been another universe collapsing in on itself. However, until we gather empirical evidence or develop a more complete model of cosmic origins, the question of what existed before the Big Bang remains a tantalizing enigma, stirring the curiosity and imagination of scientists and enthusiasts alike. The idea of multiple Big Bangs leading to multiple universes is a fascinating concept that taps into the mystery of the cosmos. The traditional view of the Big Bang describes it as the singular event that gave birth to our universe, marking the beginning of space, time, and all the matter we know today. However, some scientists propose a broader perspective known as the multiverse theory. Imagine our universe as a bubble floating in an expansive sea. According to the multiverse concept, there could be countless other bubbles, each representing a different universe, possibly formed by their own Big Bangs. These universes could have varying physical laws, constants, and conditions, leading to diverse realities beyond our own. Each bubble's formation might arise from different cosmic events or inflationary processes that occurred in the early universe, where rapid expansion could create numerous independent universes. While this theory is captivating, it remains largely speculative and lacks direct empirical evidence. Scientists are exploring ways to test these ideas through advanced cosmological observations and theoretical models. This exploration may reveal whether our universe is truly unique or just one among an infinite ensemble of realities, each shaped by its own fundamental forces and histories. The quest to understand if we live in a multiverse continues to challenge and expand our understanding of existence itself. The laws of physics are fundamental principles that describe the nature of the universe. Their origin is closely tied to the inception of the universe itself, beginning with the Big Bang. This monumental event marked the birth of space, time, and the vast array of energy and matter that compose everything we know. In the moments following the Big Bang, the universe was an unimaginably hot and dense environment. As it expanded, conditions cooled, allowing particles to form. It was during this cooling phase that the basic forces of nature began to emerge. Scientists posit that four fundamental forces govern the interactions of matter: gravity, electromagnetism, and the strong and weak nuclear forces. These forces did not just appear out of nowhere. Instead, they manifested from the underlying structure of the universe as it evolved. As the universe continued to expand and cool, more complex structures began to form. Atoms developed, leading to the creation of stars and galaxies. Throughout this process, the laws of physics began to express themselves more definitively. For instance, Gravity shaped the orbits of celestial bodies, while electromagnetism dictated the interactions of light and matter. What makes these laws so compelling is their consistency. For example, the same gravitational force that keeps planets in orbit is the same force acting on an apple falling from a tree. This universality suggests that the laws of physics arise from deeper underlying principles that govern all interactions across the cosmos. Moreover, the formulation of these laws is a continuous process through observation and experimentation. As humanity has advanced, scientists have developed mathematical frameworks to describe these laws, leading to better predictions about natural phenomena. This scientific inquiry is not merely about finding answers, but understanding the why behind these laws, revealing the intricate tapestry of interconnections that sustains our universe. The laws of physics are both a reflection of the cosmos and a guide for uncovering its mysteries, allowing us to make sense of our place within this vast expanse. Time, as we understand it, is deeply intertwined with the fabric of the universe. It's not merely a linear progression from past to present to future, but a dimension that interacts with space itself to form what we call spacetime. Imagine spacetime as a giant, flexible sheet, where the presence of matter, like stars and planets, causes the sheet to bend and curve. This bending affects how time flows. Near massive objects, time moves more slowly compared to areas further away, an observation confirmed through experiments with precision clocks. The question of whether time existed before the universe began is profound and challenging. According to many scientific theories, particularly the Big Bang model, our universe, including the passage of time, began from an extraordinarily hot and dense state approximately 13.8 billion years ago. Before this moment, the very concept of time as we know it may not have existed. Instead, there was a singularity, a point where classical ideas of space and time break down. Some theories, such as those involving quantum mechanics, suggest alternative possibilities. They propose that time could have a more discontinuous nature or could even be cyclical, suggesting the universe could undergo a series of expansions and contractions. However, these notions remain speculative. The nature of time continues to be a topic of intense study, capturing the minds of physicists and philosophers alike. Ultimately, time may be both a fundamental aspect of our reality and a construct that reflects our experience of change and events. Understanding its essence, especially regarding its relationship to the beginning of the universe, remains one of the deepest mysteries in cosmology. The concept of a higher dimensional being or force creating the universe invites us to explore the very nature of existence itself. Our universe, as we perceive it, exists in 3 spatial dimensions and unfolds over time, but theories in physics suggest that more dimensions could exist beyond our awareness, possibly influencing our reality in ways that we have yet to fully comprehend. One idea in theoretical physics posits that additional dimensions could underpin the laws of nature. In these frameworks, such as string theory, the fundamental building blocks of reality are tiny, vibrating strings that require multiple dimensions to fully manifest. If these extra dimensions exist, a higher dimensional force might influence the initial conditions of our universe, leading to its expansion and the emergence of matter and energy. Imagining a higher dimensional being brings a layer of complexity to this discussion. Such a being might operate outside the confines of our understanding, manipulating the threads of reality in ways that appear miraculous or divine from our 3-dimensional perspective. By accessing these additional dimensions, this higher being could theoretically craft the universe and its intricate laws, much like an artist forging a masterpiece with unseen tools. However, entertaining such ideas necessitates a clear distinction between scientific speculation and philosophical or metaphysical belief. Currently, there is no empirical evidence to confirm the existence of higher dimensions or beings therein. Nevertheless, exploring these possibilities can enrich our understanding of the universe and highlight the limits of human comprehension. As we delve deeper into the mysteries of existence, the boundaries between science, philosophy, and the nature of reality continue to blur, inviting awe and wonder about the true origins of our universe. The shape of the universe is one of the most intriguing questions in modern cosmology. Scientists have proposed three main possibilities: flat, open, and closed, each of which describes how the universe behaves on a grand scale. Imagine the universe as a vast surface where its shape is determined by the total amount of matter and energy it contains. If the universe is flat, it means that parallel lines will continue indefinitely without ever converging or diverging. In this scenario, the geometry follows the rules of classical Euclidean space, like the surface of a flat sheet of paper. An open universe, on the other hand, resembles a saddle or the surface of a Pringle chip. In this shape, parallel lines gradually diverge. This indicates that the universe will expand forever and will eventually become cooler and emptier over time. A closed universe is akin to the surface of a sphere. Here, parallel lines eventually converge, suggesting that the universe has enough matter and energy to stop its expansion and eventually collapse back in on itself in a so-called Big Crunch. Current observations, particularly from the cosmic microwave background radiation, suggest that our universe is very close to flat, though it may possess slight curvature. This ongoing exploration reveals that the true nature of the universe's shape not only connects to its current state, but also gives insight into its future evolution, a captivating journey toward understanding our cosmic home. The universe is astonishingly vast, a realm so large that it seems almost unimaginable. Picture the night sky filled with countless stars. These are just a fraction of what exists beyond our sight. To grasp its scale, think of the universe as an ever-expanding canvas. Keeping this in mind, scientists estimate that the observable universe stretches across a distance so substantial that light, traveling from one end to the other, would take billions of years. We can perceive a limited portion of the universe, but what lies beyond that is still shrouded in mystery. As for whether the universe has an edge, the answer ventures into the realm of speculation and theory. Current understanding suggests that if the universe does have boundaries, they are not like the edges of a simple object. Instead, it's likened to the surface of a balloon. Imagine blowing up a balloon. As it expands, every point on its surface moves away from every other point. In this analogy, the surface has no edge, providing an endless expanse to explore. Furthermore, some theories propose that if one could journey far enough in a specific direction, they might eventually return to their starting point, a concept often referred to as a closed universe. This idea leads to fascinating questions about whether our universe loops back on itself. Ultimately, the universe remains one of the last great frontiers of human understanding. It challenges our perceptions and pushes the limits of our imagination, leaving us with more questions than answers about its true nature and the possibility of realms beyond our observations. What lies beyond the observable universe is one of the most intriguing mysteries in cosmology. The observable universe is essentially the part of the cosmos that we can see, limited by how far light has traveled since the universe began. But what lies beyond this boundary remains largely unknown. The universe itself is thought to be much larger than the portion we can observe. Beyond our observational limits, there may be countless galaxies, stars, and potentially even more exotic celestial phenomena. Not just that, the universe could be expanding infinitely. In such a scenario, some regions might be so distant that their light hasn't reached us yet, meaning they are forever beyond our observational reach. One interesting concept revolves around the idea of a uniform universe. The cosmological principle suggests that, on a large scale, the universe is homogeneous and isotropic. This means that no matter which direction we look, the universe looks roughly the same. So, it's reasonable to propose that if we could see beyond our observable limits, we would encounter the same structures we see today: a sea of galaxies, dark matter, and cosmic filaments threading through the vastness of space. Furthermore, some theories suggest there might be more than one universe, a multiverse. In this view, the universe we inhabit may be just one of many. each potentially operating under different physical laws or constants. Though this idea stretches the boundary of conventional science, it opens fascinating possibilities for what could exist beyond our current horizon. The quest to understand beyond the observable universe fuels scientific inquiry and imagination. The quest to understand beyond the observable universe fuels scientific inquiry and imagination. While we might not have direct evidence of what lies beyond, exploring these intellectual frontiers continues to challenge our understanding of the cosmos. Ultimately, whether more galaxies, alternate universes, or brand new realms, the topic invites both curiosity and wonder into the nature of existence itself. The concept of hidden dimensions is a fascinating area of modern physics that stretches our understanding of the universe. Our familiar three dimensions of space, length, width, and height, only scratch the surface of what might exist beyond our perception. Theories suggest there could be additional dimensions that are compacted or curled up so tightly that they elude our senses and instruments. To picture this, imagine a garden hose from a distance. It looks like a one-dimensional line. However, when getting closer, you can discover that it actually has a circular shape, giving it another dimension. Similarly, extra dimensions, if they exist, might be present in ways we cannot easily observe. These hidden dimensions arise most prominently in string theory, a theoretical framework attempting to unify all fundamental forces and particles of nature. String theory proposes that instead of being point-like particles, the building blocks of the universe are tiny strings vibrating at different frequencies. For these strings to exist harmoniously, some theories require the existence of up to 10 or more dimensions, with the extra ones tightly compacted in ways that don't interfere with our current understanding of physics. While these dimensions remain largely theoretical, they offer intriguing possibilities for explaining phenomena that often baffle scientists, such as the interplay between gravity and quantum mechanics. Experiments and observations continue to target evidence for these dimensions, as detecting them would fundamentally change our comprehension of reality and open new avenues of exploration. As our tools and technologies evolve, we may someday glimpse these elusive dimensions, revealing a deeper fabric of the cosmos. Dark matter is an elusive and fascinating component of our universe, making up a significant portion of its total mass. While we cannot see dark matter directly, scientists have inferred its presence and distribution through its gravitational effects on visible matter. Imagine a cosmic web where galaxies and larger structures form nodes connected by filaments. Dark matter forms the backbone of this web, creating a scaffolding that guides the formation and evolution of galaxies. Most of the dark matter in the universe is not uniform. Instead, it exists in clumps and halos surrounding galaxies. These halos can be visualized as vast, invisible spheres that envelop galaxies, exerting gravitational forces that influence their motion. When scientists observe the speed at which galaxies rotate, it becomes clear that there is not enough visible mass to account for the observed speeds. The extra mass, attributed to dark matter, helps hold galaxies together, preventing them from flying apart. On a larger scale, dark matter is distributed unevenly across the cosmos. In regions like galaxy clusters, dark matter tends to be more concentrated, leading to gravitational effects that can be detected by observing how light from distant galaxies bends around these clusters, a phenomenon known as gravitational lensing. This distortion reveals the presence and density of dark matter, allowing researchers to map its distribution. Overall, dark matter shapes the structure of the universe itself, influencing how galaxies cluster and collide. Its presence drives the dynamics of cosmic evolution, highlighting its critical role in the fabric of our universe, even if it remains one of the biggest mysteries in modern astrophysics. Dark matter is an enigmatic component of our universe, comprising a significant portion of the cosmos while remaining invisible and undetectable through traditional means. Unlike ordinary matter that makes up stars, planets, and living beings, dark matter does not emit, absorb, or reflect light, making it inherently elusive. Scientists theorize that it could be composed of yet-to-be-discovered particles that interact with regular matter primarily through gravity. One leading hypothesis suggests that dark matter could be made of particles called WIMPs, or weakly interacting massive particles. These would be heavier than protons, but only interact weakly with other particles. Imagine trying to detect someone in a crowded room who speaks softly and only occasionally gestures. This is analogous to how current instruments struggle to find dark matter particles. Another intriguing possibility includes axions, hypothetical particles that are even lighter than electrons. If axions exist, they could form what is known as a sea of dark matter, permeating the universe like a fog. Despite numerous experiments aimed at detecting these particles, direct evidence remains elusive. Instead, scientists rely on the gravitational effects that dark matter has on visible matter, such as the way galaxies rotate, or how light bends as it passes near massive objects. These observations provide critical clues, suggesting that while dark matter eludes direct observation, its presence is a dominant force shaping the fabric of the universe. Understanding its exact composition could unlock many mysteries of the cosmos and our own existence within it. Dark matter is one of the universe's greatest mysteries, and its elusive nature raises many questions about how it behaves. To start, normal matter, the stuff that makes up stars, planets, and everything we see around us, interacts with fundamental forces like electromagnetism, which creates a range of observable effects such as light and heat. In contrast, dark matter does not interact through electromagnetism. This means it does not emit, absorb, or reflect light, making it invisible and difficult to detect directly. Instead, dark matter interacts primarily through gravity. It exerts gravitational pull and affects the motion of galaxies and galaxy clusters, but this interaction happens subtly compared to the strong forces that govern normal matter. Imagine a crowd of people moving in a room where some are engaged in conversation. Those conversations create audible sounds and interactions. If a few people in the crowd were completely silent and unresponsive, you would notice they are present only by observing their effect on the movement of others around them, such as the crowd shifting in response to their position without them engaging directly. In the universe, dark matter's gravitational influence is essential for explaining phenomena such as the rotation speeds of galaxies. Without it, these galaxies would spin apart because the gravitational forces from their visible matter wouldn't be enough to hold them together. The absence of electromagnetic interaction is what keeps dark matter hidden from our observations, and it's this unique characteristic that makes it fundamentally different from the everyday matter we encounter. Scientists are continuously refining their understanding of dark matter, and its role may still hold many surprises as they explore the underlying structure of the cosmos. The mystery of dark matter intrigues scientists and cosmologists as it makes up a significant portion of the universe's mass, yet eludes direct detection. Imagine a vast cosmic puzzle where most of the pieces are invisible. Dark matter is believed to exist because of its gravitational effects on galaxies and galaxy clusters, shaping their movements and formations. One of the leading hypotheses suggests that dark matter could be made up of a new type of particle, something yet to be identified and understood. These particles wouldn't interact with light in the way normal matter does, which is why they remain unseen. They might interact with existing particles through weak forces, reminiscent of ghostly shadows passing unnoticed in a brightly lit room. Alternatively, some theories propose that dark matter could derive from a fundamental force or a modification of gravity itself. This involves the idea that our current understanding of gravity might change on a cosmic scale, allowing for different behaviors in the universe that don't conform to our established laws. Exploring dark matter means delving into uncharted territory of physics. Just as scientists have discovered new particles before, like the Higgs boson, the possibility remains that dark matter represents another revolutionary discovery waiting to be uncovered. As experiments progress and technologies advance, the quest continues to unveil the nature of dark matter, potentially reshaping our understanding of the universe and the very laws that govern it. Dark energy is a mysterious force that permeates the universe, driving it to expand at an ever-increasing rate. To understand this phenomenon, imagine the universe as a balloon that is being inflated. Initially, the expansion occurs steadily, but at some point it begins to speed up dramatically. That is where dark energy comes into play. This form of energy is thought to make up a significant portion of the universe, possibly around 70% of its total energy content. While we can observe its effects, dark energy remains elusive, and scientists have yet to understand its true nature. One of the prevailing theories suggests that dark energy is a property of space itself. As more space emerges, it creates additional dark energy, resulting in an acceleration of the expansion. The most compelling evidence for this accelerating expansion of the universe comes from distant supernovae, which are stellar explosions of remarkable brightness. Observations show that these distant supernovae are fainter than expected, indicating they are farther away than they would be if the universe's expansion was slowing down. This unexpected faintness points towards a force, dark energy, that pushes galaxies apart with greater strength over time. Dark energy acts against gravity, which tries to pull matter together. The battle between dark energy's expansive nature and gravity's contracting force results in our universe's fascinating and accelerating tapestry of galaxies, forever stretching outward into the cosmos. Understanding dark energy remains one of the greatest challenges in modern physics, as it reshapes our understanding of the universe's fate. Dark energy remains one of the most enigmatic components of our universe, believed to be responsible for the accelerated expansion of space. Imagine the universe as a balloon being inflated. Instead of slowing down as one might expect due to gravitational forces, it is expanding at an increasing rate, suggesting something unseen is at work. While we often think of our three dimensions of space and one of time, some theories propose that dark energy could indeed hint at influences from alternate or higher dimensions beyond our perception. To understand this idea, consider that in addition to the familiar dimensions, there might be dimensions that we do not directly experience. These extra dimensions could interact with our own in ways that affect gravity and the fabric of spacetime. Picture it like a piece of fabric with multiple layers. When you press down on one layer, it can create ripples in another. Likewise, if higher dimensions exist, they could exert influences that manifest as the mysterious force we observe as dark energy. Investigations into concepts such as string theory propose that the universe might have more dimensions than we can observe, and certain properties of these dimensions could act like a reservoir of energy. If this energy were to leak into our three-dimensional universe, it could be perceived as dark energy driving the universe's expansion. Thus, while dark energy is fundamentally challenging our understanding of physics, the notion that it might signal the presence of higher dimensions opens avenues of exploration and speculation in cosmology. This convergence of ideas is a testament to the complexities of our universe, hinting that reality may be far richer than we currently comprehend. Inside a black hole, the laws of physics as we know them begin to break down, leading to a realm of extreme conditions that is difficult to fully comprehend. When matter falls into a black hole, it approaches a point of no return known as the event horizon. Here, the gravitational pull is so intense that nothing, not even light, can escape. This creates a region that is entirely dark and hidden from our view. As objects cross the event horizon, they are inexorably drawn towards the center of the black hole, where it is believed that all the black hole's mass is concentrated in an infinitely dense point called a singularity. At this singularity, gravity becomes infinitely strong, and space and time are distorted beyond any familiar understanding. In this extreme environment, it is theorized that all known laws of physics cease to function as they do in our universe. Interestingly, outside the event horizon, the black hole's powerful gravitational influence continues to affect surrounding space. Time itself is also impacted dramatically, While someone falling into the black hole would experience time normally until they reach the singularity, an outside observer would see their descent slow down and eventually freeze as they approach the event horizon, making it seem like they are suspended in time. While these phenomena give us a glimpse into the bizarre physics of black holes, the true nature of what occurs inside remains one of the great mysteries of modern astrophysics, provoking questions that challenge our understanding of space, time, and the universe itself. Inside a black hole, the laws of physics as we know them begin to break down, leading to a realm of extreme conditions that is difficult to fully comprehend. When matter falls into a black hole, it approaches a point of no return known as the event horizon. Here, the gravitational pull is so intense that nothing, not even light, can escape. This creates a region that is entirely dark and hidden from our view. As objects cross the event horizon, they are inexorably drawn towards the center of the black hole, where it is believed that all the black hole's mass is concentrated in an infinitely dense point called a singularity. At this singularity, gravity becomes infinitely strong, and space and time are distorted beyond any familiar understanding. In this extreme environment, it is theorized that all known laws of physics cease to function as they do in our universe. Interestingly, outside the event horizon, the black hole's powerful gravitational influence continues to affect surrounding space. Time itself is also impacted dramatically. While someone falling into the black hole would experience time normally until they reach the singularity, an outside observer would see their descent slow down and eventually freeze as they approach the event horizon, making it seem like they are suspended in time. While these phenomena give us a glimpse into the bizarre physics of black holes, the true nature of what occurs inside remains one of the great mysteries of modern astrophysics, provoking questions that challenge our understanding of space, time, and the universe itself. The concept of a black hole is steeped in mystery, and one of the most intriguing questions is whether anything, including information, can escape from it. To understand this, it's essential to consider the nature of black holes. Formed from the remnants of massive stars that have collapsed under their own gravity, black holes possess an incredible gravitational pull. This pull becomes so intense that not even light, the fastest thing in the universe, can break free once it crosses a boundary called the event horizon. At the event horizon, the escape velocity exceeds the speed of light, creating a sort of one-way door. Once anything crosses this threshold, it is effectively cut off from the rest of the universe. This has led to the famous statement that nothing can escape a black hole, including light, and by extension, any information carried by that light. However, in recent years, physicists have delved into the implications of this. They explore the theory of black hole evaporation proposed by Stephen Hawking. His insights suggest that black holes are not entirely black. They can emit radiation due to quantum effects near the event horizon. This radiation, known as Hawking radiation, implies that black holes might slowly lose mass and could eventually evaporate completely. However, even if a black hole were to shrink, the information it consumed appears to be lost to the universe, raising profound questions about the nature of information and its conservation. The dilemma surrounding black holes and information leads to intense debates among scientists. It challenges fundamental principles of physics, particularly how information is treated in the universe. While current understanding posits that no information can escape once it enters a black hole, researchers continue to probe the nature of reality, seeking a deeper understanding of what happens at a black hole's core, one of the most enigmatic realms in astrophysics. The idea that black holes could serve as gateways to other universes or dimensions is a captivating notion, often portrayed in science fiction. However, when we explore the realities of black holes through the lens of scientific understanding, the picture becomes more complex. Black holes are regions in space where gravity pulls so intensely that nothing, not even light, can escape. They are born from the collapse of massive stars under their own gravitational force. At the core of a black hole lies what is known as a singularity, a point where the laws of physics as we understand them break down. Surrounding the singularity is the event horizon, which marks the point of no return. Once something crosses this boundary, it cannot escape the black hole's gravitational pull. The extreme conditions present within this environment raise intriguing questions about the nature of space and time. Some theories suggest that, hypothetically, the environment inside a black hole could alter the fabric of space-time to such an extent that it might connect to another universe, creating a sort of tunnel. This concept is often compared to the idea of a wormhole, a hypothetical passage through space-time that could potentially link disparate areas of our universe or even different universes altogether. However, these ideas remain speculative. Current understanding of physics, particularly general relativity, does not provide solid evidence for black holes acting as portals to other realms. Instead, the complexities of what happens inside a black hole are still largely a mystery. The extreme conditions within can lead to various theoretical implications, including the possibility of a firewall, an area where incoming matter meets an abrupt end, or the preservation of information, which remains hotly debated among physicists. While the notion of black holes leading to other universes is an exciting thought, it remains in the realm of speculation and theoretical physics. Our understanding of these mysterious cosmic phenomena continues to evolve as we advance our exploration of the universe and the laws governing it. Supermassive black holes, those mysterious giants lurking at the heart of most galaxies, are believed to have complex origins that intertwine with the evolution of galaxies themselves. The story begins in the early universe, shortly after the Big Bang. After the initial expansion, regions of gas and matter coalesced due to gravity, forming the first stars. Some of these stars grew massive and, upon exhausting their nuclear fuel, collapsed under their own weight, leaving behind black holes. As these stellar black holes formed, they didn't stay isolated. Over millions of years, they began to merge with each other or consume surrounding material, growing larger in the process. Picture this as a cosmic feeding frenzy, where every merger and ingestion of gas adds to their mass. In environments rich with gas and stars, like dense stellar clusters, this growth accelerates. Simultaneously, galaxies themselves were forming and evolving, often colliding and merging with one another. Such dramatic events significantly influenced the dynamics at their centers, funneling gas and dust toward the gravitational pull of the emerging black holes. This process, known as accretion, allows the black holes to accumulate vast amounts of matter, boosting their size. Over time, these black holes grow to incredible proportions, becoming supermassive, their masses equivalent to millions or even billions of times that of our Sun. The relationship between supermassive black holes and their host galaxies is reciprocal. While black holes influence the evolution of their galaxies through energetic jets and radiation, the structure and dynamics of the galaxies help create the conditions for the black hole's continued growth. This intricate dance showcases a fundamental connection between the components of the universe, highlighting how galaxies and supermassive black holes shape each other over eons, resulting in the intricate cosmos we observe today. Primordial black holes are intriguing cosmic objects that could potentially provide insights into the nature of dark matter. To understand this, we first need to grasp what dark matter is. A mysterious form of matter that doesn't emit or absorb light, making it invisible and detectable only through its gravitational effects on visible matter. It's believed to make up a significant portion of the universe, yet its exact composition remains elusive. Now, primordial black holes are theorized to have formed shortly after the Big Bang in the hot and dense conditions of the early universe. They could have originated from fluctuations in energy density, collapsing into black holes before stars and galaxies had the chance to form. These ancient black holes would vary in size, from very small to potentially massive, but unlike the black holes formed from dying stars, they wouldn't be concentrated in specific areas. If primordial black holes exist, they could contribute to the shadowy mass attributed to dark matter. The idea is that, although they are incredibly small and not easily detectable by traditional astronomical methods, Their collective gravitational influence could help explain the behavior of galaxies and the large-scale structure of the universe. Essentially, if enough primordial black holes could be found, they might account for some or all of dark matter's effects. However, the search for primordial black holes poses challenges. Scientists have yet to observe one, as they can be difficult to identify. While certain signals like gravitational waves might hint at their presence, conclusive evidence is still required. The relationship between primordial black holes and dark matter is an exciting area of research, representing a potential bridge between two significant areas of astrophysics: the origin of black holes and the quest to unveil the underlying composition of the cosmos. The question of whether we are alone in the universe intrigues scientists, philosophers, and curious minds alike. When we gaze into the night sky, filled with countless stars and galaxies, it raises profound possibilities about life beyond Earth. The universe is vast, with billions of galaxies, each containing millions or even billions of stars. Many of these stars are orbited by planets, some of which may lie within a habitable zone where conditions could allow for liquid water, a crucial ingredient for life as we know it. Scientists employ a variety of methods to search for signs of extraterrestrial life. For instance, missions exploring Mars aim to uncover any past or present microbial life. Similarly, telescopes examine exoplanets, those planets outside our solar system, analyzing their atmospheres for chemical signatures that might indicate the presence of life. The discovery of extremophiles, organisms on Earth that thrive in harsh environments, serves as a reminder that life can exist in conditions previously thought to be uninhabitable. However, despite extensive searching, we have yet to find conclusive evidence of extraterrestrial life. The universe's vastness and the limitations of our current technology make it challenging to investigate all possibilities thoroughly. Furthermore, the seeming rarity of intelligent civilizations raises the question of whether complex life is common or extraordinarily rare. In search of answers, projects like SETI, the search for extraterrestrial intelligence, utilize radio telescopes to listen for signals from other civilizations. So far, these efforts have not yielded any confirmed communications. This leads to the possibility that other intelligent beings may be out there, but are either too far away, not using technology we can detect, or may have existed in the past and gone extinct. While we have not found definitive evidence of life beyond Earth, the potential remains high within the enormity of the cosmos. The ongoing exploration and discovery continue to fuel our understanding, reminding us that the universe is an expansive realm of mystery yet to be fully unveiled. The existence of life as we know it hinges on a delicate interplay of several fundamental conditions. To start, a stable environment is crucial, which includes a suitable temperature range. This allows for the presence of liquid water, often described as the universal solvent. Without water, essential biochemical reactions cannot occur, making it nearly impossible for life to thrive. Additionally, the chemical building blocks of life must be present. These include essential elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements combine in various ways to form intricate molecules like proteins and nucleic acids, which are vital for cellular functions and genetic information. Another key aspect is a source of energy to drive metabolic processes. On Earth, sunlight is the most abundant energy source, fueling photosynthesis in plants, which in turn supports the entire food web. However, in other environments, such as deep-sea hydrothermal vents, organisms rely on chemical energy from minerals instead. To sustain life over time, a stable atmosphere plays a significant role, providing necessary gases like oxygen for respiration and carbon dioxide for photosynthesis. It also offers protection from harmful cosmic radiation and helps regulate temperature through greenhouse effects. Lastly, a planet must possess a geologically active environment, which allows for recycling of materials and maintenance of chemical cycles. This dynamism fosters diverse ecosystems as it constantly introduces new habitats and species interactions. The right temperature, presence of liquid water, vital elements for chemistry, sources of energy, a protective atmosphere, and geologic activity all converge to create a cradle for life to flourish. Understanding these conditions not only illuminates our own existence, but also guides the search for life beyond our planet. Life, as we understand it, can indeed thrive in extreme environments, and places like Titan and Europa provide fascinating examples of such possibilities. Titan, Saturn's largest moon, has a dense atmosphere primarily made of nitrogen, with lakes and rivers of liquid methane and ethane on its surface. While this environment is drastically different from Earth, the presence of organic compounds and a stable environment suggests that life could adapt to use these hydrocarbon lakes in ways that we cannot yet fully comprehend. Europa, one of Jupiter's moons, presents an even more intriguing scenario. Beneath its icy shell, which is several miles thick, lies a vast ocean of liquid water. This ocean is kept warm by tidal heating generated by the gravitational pull of Jupiter, creating conditions that might be suitable for life. The ocean could harbor chemical processes similar to those found in Earth's deep-sea hydrothermal vents, where life thrives in total darkness, relying on chemosynthesis rather than sunlight. Both Titan and Europa challenge our understanding of life by suggesting that it could exist independently from the conditions on Earth. There may be forms of life that require different solvents for biological processes or utilize alternative biochemical pathways. If life exists on these moons, it might not resemble anything we know, but it could be a testament to life's resilience and adaptability in the universe. The ongoing exploration of these moons by missions like the Europa Clipper aims to uncover deeper insights into these extreme habitats and their potential to host living organisms. The appearance of intelligent extraterrestrial life is a topic of immense speculation, shaped by our understanding of biology, evolution, and the diverse environments that might exist across the universe. One important aspect to consider is that life evolves to survive in specific conditions. For example, beings from a planet with a dense atmosphere and extreme pressure might develop robust exoskeletons to withstand those forces, while organisms in a world with lower gravity could potentially be taller and more elongated. When envisioning extraterrestrial intelligence, we must also consider the range of biochemistries that could arise. While Earth life is carbon-based and relies on water as a solvent, other forms of life could utilize different elements. For instance, silicon-based life has been theorized, fundamentally altering the structural makeup of creatures. This could lead to beings that look entirely foreign, perhaps with a glimmering crystalline quality. Sensory perception might also evolve differently, depending on the environment. Life worlds immersed in darkness could lead to species with highly developed tactile senses or infrared vision. In contrast, those on bright sunlit planets might rely heavily on visual signals, leading to beings with pronounced eyes or outer structures designed to focus light. Furthermore, intelligence doesn't necessarily mean human-like features. Beings might possess several limbs, unique modes of communication, or even forms of consciousness that don't mirror our own. In an aquatic environment, for example, intelligent life forms could have streamlined bodies with adaptations for both swimming and complex social interaction, such as emitting bioluminescent signals to communicate. It's also possible that intelligent extraterrestrial life may not have a physical form as we perceive it. Some hypotheses suggest the existence of energy-based entities that operate differently, without physical limitations. This invites us to rethink our definitions of intelligence and sentience. Ultimately, the specifics of intelligent extraterrestrial life are deeply tied to the environmental pressures, evolutionary history, and biological resources available on their homeworlds. The possibilities are as varied as the stars in the sky, each waiting to be discovered. The hunt for extraterrestrial civilizations is a quest fraught with both excitement and uncertainty. Currently, scientists have been diligently scanning the cosmos for signals, messages, or evidence that might indicate intelligent life beyond Earth. However, there remains a tantalizing possibility that we may have overlooked signs of these civilizations. First, let us consider the vastness of space itself. The universe is incredibly large, with billions of galaxies, each containing billions of stars and potentially even more planets. This sheer scale makes it exceptionally challenging to search every nook and cranny for signs of life. Our current technology allows us to monitor only a small fraction of the sky at any given time, meaning that we may simply not be looking in the right place or at the right moment. Another aspect to consider is the nature of communication. Advanced civilizations might not use radio waves or light signals like we do. They could have developed technologies far beyond our current understanding or might communicate in ways that are entirely foreign to us. Imagine a civilization using a type of energy or communication that we haven't even discovered yet, thus rendering their signals undetectable by our instruments. Additionally, the timescales involved in cosmic development are staggering. Civilizations rise and fall over millions of years, so the chance of us existing simultaneously with another intelligent species might be slim. It's possible that a civilization could have thrived and then extinguished itself long before we even began our search. Moreover, even if we detect phenomena that seem unusual or intriguing, interpreting them correctly poses another challenge. Some signals might be natural occurrences misidentified as artificial, leading us to dismiss actual signs of intelligence. The ability to differentiate between the two requires constant refinement of our methods, reinforcing the possibility that we might have missed critical clues. Lastly, there's the idea that advanced civilizations may deliberately choose to remain undetected. Just as we often keep our activities private, it's plausible that an extraterrestrial society may have reasons to avoid revealing their presence. Their motives could range from self-preservation to a belief that interactions with other civilizations could have dire consequences. In conclusion, while we've made considerable strides in our search for signs of extraterrestrial life, many possibilities remain. The universe holds countless mysteries, and the signs of intelligent civilizations could be out there, waiting for us to refine our approach and expand our understanding of what forms those signs might take. The journey continues, with each discovery potentially bringing us closer to answering one of humanity's most profound questions. Are we alone in the universe? The search for extraterrestrial life is one of the most ambitious endeavors undertaken by scientists, and despite decades of exploration, we have yet to uncover definitive evidence of life beyond Earth. This quest faces numerous challenges. Firstly, the vastness of the universe plays a crucial role. Picture a limitless expanse filled with countless stars, many of which host their own planetary systems. The distances between these celestial bodies are immense, making it incredibly difficult to explore many of them directly. Moreover, consider the specific conditions required for life as we know it. Life thrives in certain environments, typically where there is liquid water, appropriate temperatures, and essential chemical elements. The search primarily focuses on planets and moons within the so-called habitable zone, where conditions might be just right. Yet, even on those worlds, life could exist in forms radically different from what we understand, possibly thriving in environments considered extreme by our standards. Additionally, the methods we currently employ to search for alien life, such as monitoring radio signals or scanning for biosignatures in planetary atmospheres, are limited by technology and the understanding of potential life forms. We might simply be looking for signs of life in ways that do not align with how life might manifest elsewhere. Lastly, it's plausible that intelligent civilizations may be exceedingly rare or have short lifespans relative to the age of the universe. They might also be using forms of communication or technology that we have not yet developed the capability to detect. In that immense cosmic backdrop, the absence of discovered extraterrestrial life could be seen as a reflection not of its non-existence, but rather the complexities inherent in this grand search. The journey continues as we keep expanding our understanding and refining our techniques, always hopeful of one day unraveling the mystery of life beyond our planet. The question of whether humanity could be the first intelligent civilization in the universe is both thrilling and thought-provoking. To grasp this idea, one must consider the vastness of the cosmos. Our galaxy, the Milky Way, contains billions of stars, many of which host planets. Some of these planets lie within what scientists call the habitable zone, where conditions might allow life to thrive. The conditions necessary for developing intelligent life involve a series of complex processes, including the formation of stable planetary environments, the emergence of basic life forms, and then the transition to more complex organisms. Each step in this progression is subject to numerous variables, making the rise of intelligence a unique phenomenon. While it is entirely possible that other intelligent beings exist in distant corners of the universe, the sheer enormity of space, coupled with the vast amount of time since the universe began, suggests that many civilizations may have risen and fallen long before us, or might still be on their path to evolution. Moreover, our attempts to find evidence of other intelligent life through methods like sending signals into space or listening for extraterrestrial communications often lead to silence. This could imply that intelligent civilizations are incredibly rare, or that they do not last long enough to make contact. Ultimately, while we hold the potential title of the first intelligent civilization, the universe remains full of mysteries. The absence of proof doesn't mean we are alone. It merely prompts further exploration into the profound question of life's existence beyond our home planet. Thus, while the notion of being the first is exhilarating, it also reminds us of our collective quest for knowledge in the vast, uncharted realms of the universe. The idea that advanced civilizations might be avoiding contact with us is a fascinating one. One theory suggests that if such civilizations exist, they may be deliberately choosing not to communicate with humanity, possibly because they are observing us, much like we observe wildlife in nature. This could be due to a principle similar to a cosmic version of a prime directive, where interference with less advanced cultures is avoided to allow for natural development. There are also practical considerations. Advanced civilizations may have vastly different priorities and ways of life, leading them to view us as insignificant. From their perspective, engaging with humanity might not present any benefits worth the risk of exposure. Furthermore, the vastness of space presents a staggering challenge. They might not even be aware of our existence amidst the countless stars. Another possibility is that civilizations could be extremely rare. The immense distances between stars and the relatively brief window of time during which intelligent species exist make the chances of two civilizations being active at the same moment and intersecting in space or time very slim. This cosmic solitude could mean that, even if they are out there, we just happen to be in separate parts of the universe, focused on our own development. In more speculative terms, some suggest that advanced civilizations might be pursuing self-imposed isolation to avoid hostile interactions, preferring to remain in the background rather than risk confrontation with a less developed species. This combination of factors leads to the intriguing possibility that rather than being ignored, we might simply be on the fringes of a cosmic community that chooses not to engage with us at this moment in time. The possibility that alien signals could be hiding in plain sight is a fascinating one, inviting us to consider how we interpret the vast ocean of cosmic information. The universe emits an incredible variety of signals, ranging from radio waves to light across the spectrum. But it's not just the traditional signals we might expect that could contain hidden messages, it's also the way these signals could be encoded. Imagine listening to music while trying to hear a specific song that blends seamlessly into a playlist. In a similar way, extraterrestrial messages could potentially be woven into natural cosmic noise. These signals may be faint, altered, or even disguised in ways that make them difficult for us to distinguish from background activity. While we primarily listen for clear, high-energy bursts or repeatable patterns, alien civilizations might utilize subtler methods, encoding information in frequencies or modulations we have yet to recognize. To decipher these potential messages, scientists employ a method called signal processing, akin to tuning a radio to isolate a specific frequency amidst static. Advanced analytical techniques search for anomalies or patterns that deviate from the norm, giving us the chance to spot that elusive signal amidst celestial chatter. Moreover, the complexity of any encoding is bound by the limits of human understanding. Patterns that seem random might actually hold intricate meanings, much like a poem hidden in a seemingly chaotic arrangement of words. Ultimately, the search for these signals is not just about the technology we possess. It's also about our creativity and adaptability in recognizing how intelligence might choose to communicate. The signals might be there, quietly waiting for a mind that can perceive them in a manner we have yet to realize. As we refine our listening techniques and expand our understanding, the potential for discovery becomes not just about finding new signals, but also about revolutionizing how we look at the universe itself. Throughout history, several natural phenomena have sparked intrigue and speculation about extraterrestrial life, often leading to misconceptions. One prime example is the appearance of unusual lights in the sky. Many people have reported seeing strange glowing objects or orbs, which, upon investigation, are often attributed to atmospheric conditions or natural events like meteors or voltage-induced plasma discharges in the atmosphere. These misleading lights, while captivating, are grounded in Earth's own physics rather than alien visitors. Another instance involves the so-called crop circles. Initially interpreted by some as messages from extraterrestrials, these intricate patterns in fields have been shown time and time again to arise from human activity, either as art or hoaxes, rather than being the work of aliens. The beauty of these designs often obscures their mundane origins, feeding the myth of alien communication. Even the mysterious sounds captured from the depths of our oceans have triggered theories of underwater alien civilizations. However, these noises could be attributed to natural phenomena such as whale songs, tectonic activity, or ice breaking apart. As our understanding of Earth's ecological and geological systems expands, many of these sounds reveal more about our planet than they do about life beyond it. Additionally, celestial events like fast radio bursts have also led to speculation about alien technology. These bursts are powerful but seem to be natural cosmic phenomena, potentially the result of neutron stars colliding or other high-energy astrophysical processes. While the search for extraterrestrial intelligence continues, the universe is full of extraordinary natural occurrences that can inspire wonder but do not imply the existence of alien life. Many instances of supposed alien evidence can often be traced back to natural explanations. As we advance in our scientific comprehension, the tendency to misinterpret these phenomena calls for ongoing inquiry and careful scrutiny, highlighting the importance of distinguishing between the extraordinary claims of alien existence and the fascinating, complex reality of our own world. Time is a fascinating concept that has sparked debate among scientists, philosophers, and laypeople alike. At its core, time can be understood as a framework that helps us organize events and experiences in a sequence: past, present, and future. This sequence allows us to measure change and understand causality, which is essential for everything from the life cycle of a star to the flow of our daily lives. From a scientific perspective, particularly in the realm of physics, time is often regarded as a fundamental aspect of the universe. In the theory of relativity proposed by Albert Einstein, time is interwoven with space to form a four-dimensional fabric known as spacetime. Objects with mass warp this fabric, creating the effect we perceive as gravity. This intertwining demonstrates that time does not exist independently. It is part of the very structure of the universe, influenced by the presence of mass and energy. However, the notion of time being an illusion emerges primarily from philosophical discussions and certain interpretations of quantum mechanics. Some theorists suggest that since all moments exist simultaneously at some level, our perception of time as a flowing entity might not align with the underlying reality. In this view, what we interpret as the passage of time could be a cognitive construct, a tool our brains use to make sense of a complex and chaotic universe. Ultimately, while time feels very real to us, the deeper we delve into its nature, the more complex and intriguing it becomes. It serves essential roles in our understanding of physics and our interactions in the world, but whether it is an absolute feature of the cosmos or merely an artifact of human consciousness remains an open question, inviting us to explore the boundaries of both science and philosophy. Time travel has long captured our imagination, first as a thrilling concept in literature and film, but also as a subject of serious scientific inquiry. At its core, the idea hinges on the nature of time itself, which is still not fully understood. Time, as we experience it, moves in a linear fashion, at least from our perspective, past to present and then to future. Scientists theorize that under certain extreme conditions, the fabric of space and time can be warped or manipulated. One such concept revolves around the aforementioned black holes, where immense gravitational forces can affect the flow of time. Near these objects, time can stretch out, creating what feels like a form of time dilation relative to observers far away. This suggests that time can behave differently under different gravitational influences. Another intriguing idea lies in the fabric of the universe itself. Some physicists propose that wormholes, hypothetical passages through space-time, could allow for shortcuts between different points in time and space. However, these wormholes are purely theoretical at this stage, and the challenges of creating or maintaining one are immense. Additionally, theories concerning the speed of light suggest that moving at such speeds could potentially lead to time travel into the future. In this context, time is less rigid and more fluid, bending and flexing under extraordinary conditions. However, practical applications of such travel remain firmly within the realm of speculation, facing monumental technical and energetic barriers. So, while the notion of time travel is exhilarating, and there are scientific principles that allow for its theoretical existence, the practical realization of time travel remains elusive. It invites us to ponder not just the possibilities of traveling through time, but also the complex nature of the universe, where the rules governing reality are still being unraveled. The flow of time is not uniform throughout the universe. It varies depending on gravitational influences and relative speed. To understand this, think of time as a flexible fabric that can stretch and compress. When a massive object, like a planet or a star, is present, it creates a gravitational field that warps this fabric. This means that the closer you are to a massive body, the more pronounced this warping effect becomes. For example, near a black hole, where gravity is extraordinarily strong, time can slow down significantly compared to areas far removed from such a massive object. An observer perched on the edge of a black hole would witness time passing much more slowly than someone far away from that gravitational influence. This principle is a cornerstone of Einstein's theory of relativity, which describes how space and time are interconnected. Additionally, the relative motion of objects further affects how time is experienced. According to the same theory, if you were to travel at speeds close to that of light, time would appear to pass more slowly for you compared to someone who remains stationary. This interplay of speed and gravity creates a complex tapestry where time is experienced differently based on one's position and motion throughout the universe. While we commonly perceive time as a constant in the broader cosmos, it is a dynamic phenomenon shaped by the forces of gravity and speed, leading to variations that can sometimes seem almost paradoxical. Yes, there are indeed regions of the universe where time behaves differently, and these phenomena can largely be attributed to the effects of gravity and the structure of space itself. To understand this, consider the idea that time is not a constant, unchanging factor, but is influenced by the presence of massive objects such as stars, planets, and especially black holes. In areas of strong gravitational pull, time can slow down significantly compared to regions with weaker gravity. This effect is described by a theory called general relativity, proposed by Albert Einstein. Imagine a clock on Earth ticking away, marking each second, while a similar clock positioned close to a massive star runs more slowly. This means that if someone were to spend time near that star and then return to Earth, they would find that less time has passed for them compared to their friends back home. This effect is often referred to as gravitational time dilation. Moreover, the universe also includes cosmic structures like black holes, where the gravitational force is so intense that it leads to extreme distortions of both space and time. Close to a black hole, time slows to such an extent that from an outside observer's perspective, it appears to come to a complete halt at the event horizon, the point of no return. This fascinating conceptual twist shows that time is inherently linked to the fabric of the universe, shifting and stretching in response to the objects within it. Yes, time can indeed behave differently in various regions of the universe due to the profound effects of gravity and spacetime, leading to strange and mind-bending experiences for those who might venture close to massive celestial bodies. The arrow of time is a fascinating concept that explores why time seems to flow in one direction, from the past to the future. To grasp this notion, we must consider the fundamental differences between time's progression and the physical laws that govern the universe. One key aspect of the arrow of time is relativity. According to this principle, time can be experienced differently depending on the observer's speed and gravitational influence, yet there remains a linear sensation of time moving forward for everyone. Another crucial element is entropy, which refers to the tendency of systems to evolve from order to disorder. In simpler terms, think of a freshly arranged deck of cards. Over time, through handling, the neat order of that deck will become increasingly chaotic. This movement toward greater disorder gives us a tangible sense of time moving forward. The universe is governed by the second law of thermodynamics, which states that in an isolated system, entropy will always increase, creating a clear distinction between the past, when things were more organized, and the future, when they become less so. Philosophical implications also accompany our understanding of the arrow of time. Many ponder why we remember the past, but never the future. Our experiences accumulate in a one-way flow, emulating the effects of entropy. This leads to further questions about consciousness and memory, complicating our grasp of time itself. While we may never completely decode the true nature of time, ongoing research in physics, cosmology, and neuroscience presents an ever-expanding window into its mysteries. Each discovery enriches our perspective, inviting us to reflect on our place in the cosmos and the ever-unfolding narrative of existence. This combination of scientific inquiry and philosophical contemplation propels us forward in our quest to understand the multifaceted arrow of time. The concept of the multiverse suggests that our universe might be just one of many, potentially an infinite number of them. To understand this idea, picture a vast cosmic landscape where each universe operates with its own set of physical laws and constants. Imagine every decision you've ever made branching out into new realities, creating parallel worlds where different outcomes have unfolded. Some scientists propose that certain theories in physics, especially those dealing with quantum mechanics and cosmology, hint at this possibility. For instance, quantum mechanics introduces the idea that particles can exist in multiple states at once until they're observed. This leads to speculation that every possible outcome occurs, resulting in different branches of reality. Furthermore, the theory of inflation, describing the rapid expansion of the cosmos after the Big Bang, supports the idea that different regions of space can undergo their own inflationary phases. This could give rise to universes that are entirely disconnected from one another. However, it's important to note that the multiverse remains a controversial and largely theoretical topic. While the idea tantalizes our imagination, as of now, we lack direct evidence to confirm its existence. The study of the multiverse opens fascinating questions about the nature of reality and our place within it. And as our scientific understanding evolves, we might inch closer to answering whether we are truly alone in this vast cosmos or part of an intricate network of universes beyond our comprehension. The concept of universes with entirely different laws of physics belongs to the intriguing realm of theoretical physics and cosmology, often referred to as the multiverse hypothesis. Imagine our own universe as a bubble in a vast sea of bubbles, each representing a different universe. While our bubble operates under a set of physical laws, like the laws of gravity and electromagnetism, other bubbles might have their own unique laws governing how matter and energy behave. In some of these hypothetical universes, gravity might be weaker or stronger, or the fundamental forces could interact in unfamiliar ways. Such variations could lead to the existence of different particle types, forms of matter, and even the potential for structures completely unlike anything we know, such as stars that behave differently or galaxies that evolve in ways contrary to our understanding. This notion opens up fascinating possibilities. For instance, in a universe without the same gravitational force we experience, planets might not form as we know them, and life, as we understand it, may never have had a chance to emerge. Conversely, other laws of physics could allow for strange, exotic forms of existence, potentially leading to life that operates on entirely different principles. While the idea of different universes is currently speculative, it invites us to question the very foundations of our reality. By exploring how these fundamental rules could vary, we can deepen our understanding of our universe and the nature of existence itself, blending scientific inquiry with the limits of human imagination. The concept of alternate universes, often referred to as parallel universes, suggests a fascinating idea that there could be other versions of reality existing alongside our own. Though this notion springs from theories in physics, including quantum mechanics, it's still largely speculative. The most commonly referenced theory, known as the multiverse theory, proposes that for every possible outcome of a decision or event, there could be a branching universe where a different outcome occurred. If alternate universes truly exist, the question of interaction becomes intriguing. To visualize this, imagine multiple books on a shelf, where each book represents a different universe, containing its own story, characters, and timelines. In theory, if these universes could interact, it might be akin to opening a book to find a character stepping onto the pages of another book. However, the mechanisms behind such an interaction remain unclear and are not currently supported by scientific evidence. Some ideas suggest that these alternate universes could occasionally collide under certain conditions, like two soap bubbles merging briefly before separating again. However, this is more of an abstract concept rather than a proven physical process. The laws of physics as we understand them, particularly general relativity and quantum mechanics, do not provide a straightforward pathway for interaction. So far, our ability to detect or access alternate universes is limited by the very fabric of our own universe, which may act like a barrier. While popular culture often portrays exciting scenarios of traveling between universes, the reality remains rooted in theoretical physics. Until we gather more understanding or evidence, the idea that alternate universes might interact with ours will continue to be a tantalizing mystery in the realm of scientific exploration and imagination. Proving the existence of a multiverse is a challenging venture in the field of theoretical physics and cosmology. The concept of a multiverse suggests that our universe is just one of many, each potentially having different laws of physics and conditions. To establish evidence for such a notion, scientists would need to explore various angles. One approach is through the study of cosmic inflation. This theory posits that the universe underwent a rapid expansion just after the Big Bang. If inflation occurred, it could lead to myriad bubble universes, each evolving independently. Detecting specific patterns or irregularities in the cosmic microwave background radiation, the afterglow of that initial expansion, could provide hints that other universes exist or had interactions with our own. Another potential avenue is through the physical laws that govern our universe. If certain constants of nature appear to be fine-tuned for the emergence of life, it might suggest that our universe is one of many, where different combinations of these constants exist. This fine-tuning could point toward a multiverse, but proving it remains difficult, as accessing these alternate realities is beyond our current technological capabilities. Quantum mechanics might also offer a pathway to the multiverse idea. Some interpretations suggest that every decision leads to branching realities, where all possible outcomes occur in separate universes. Experiments exploring quantum phenomena could selectively favor outcomes that hint at parallel realities, but concrete proof remains elusive. Ultimately, for a robust proof of the multiverse theory to be established, scientists would need both observational evidence and theoretical validation. Until then, it exists primarily as an intriguing possibility, fueling debates and research in the quest to understand our place in the cosmos. Each step we take in exploring the fabric of reality can bring us closer to potentially unveiling the secrets of a greater multiversal tapestry. The question of whether we are living in the best possible universe for life brings us to the intriguing intersection of cosmology and biology. To consider this, we should first understand some of the fundamental aspects that make our universe conducive to life as we know it. Our universe is structured in a way that allows for the formation of stars, planets, and the essential elements required for life. For instance, the existence of stars provides not only light, but also heat, which is crucial for maintaining the right conditions on planets like Earth. The formation of elements in stars through nuclear fusion creates the building blocks of life, such as carbon, nitrogen, and oxygen. Moreover, our planet sits in the so-called Goldilocks zone of our solar system, a region where the temperature is just right for liquid water to exist. Water is paramount because it acts as a solvent, facilitating chemical reactions crucial for life. Additionally, Earth has a stable climate, a protective atmosphere, and a magnetic field that shields it from harmful cosmic radiation. However, whether this universe is the best for life is a more complex matter. If we consider the vastness of the cosmos, with billions of galaxies and countless planets, the possibility exists for other life-hosting environments. Different types of stars and planets could potentially support alternative forms of life based on different biochemical processes that we might not fully understand yet. The concept of the fine-tuning of the universe comes into play here, suggesting that many physical constants and conditions appear to be finely adjusted to allow for the existence of life. If these constants were even slightly altered, the universe could turn into a barren landscape unfit for life as we know it. Yet some scientists suggest that our universe might not be singular. Rather, there could be a multiverse with varying laws of physics. In such a scenario, we just happen to reside in a universe that is friendly to life. Ultimately, while our universe boasts remarkable conditions suitable for life, determining if it is the best one involves a blend of scientific exploration and philosophical pondering. As our understanding of the universe expands, so too does our appreciation for the intricate dance of conditions that have allowed life to emerge here on Earth. Quantum entanglement is a fascinating phenomenon that challenges our understanding of how particles interact across great distances. At its core, entanglement refers to a special connection between particles, where the state of one instantly affects the state of another, no matter how far apart they are. Picture two entangled particles as two dancers who have perfectly synced their movements. A change in one dancer's position is instantly mirrored by the other, regardless of the space that lies between them. What makes this possible lies in the principles of quantum mechanics, where particles exist in a superposition of states until they are measured. When entangled particles are created, they share this superposition. That means, even if you separate them by vast distances, imagine one particle on Earth and the other in a distant galaxy. Measuring the state of one particle will immediately determine the state of the other. This process appears to defy the conventional notion that information can only travel at the speed of light, leading to what Einstein famously referred to as spooky action at a distance. Importantly, entanglement does not allow for the transfer of information in the traditional sense. The results are random. You can't control how one particle's state will influence the other's outcome. This randomness preserves the principle of causality, avoiding any paradoxes with faster-than-light communication. Instead, it suggests a deeper level of connection in the fabric of reality that we are just beginning to decipher. Thus, quantum entanglement continues to intrigue scientists and philosophers alike, raising profound questions about the nature of space, time, and the interconnectedness of the universe at its most fundamental level. The role of consciousness in quantum mechanics is a fascinating area of inquiry that straddles the line between science and philosophy. At the heart of quantum mechanics is the idea that particles, like electrons, exist in a state of uncertainty until they are measured. This means that until someone observes or measures a particle, it can be in multiple states simultaneously, a phenomenon known as superposition. Now, when we delve into consciousness, we encounter interpretations of quantum mechanics that suggest observers play a vital role in determining the state of a system. Some theorists propose that it is the act of conscious observation that collapses this superposition into a definite state. Imagine it like having a deck of cards that, when left alone, is a mix of all possible arrangements. Only when you look at it does one arrangement become visible, while the others fade away in relevance. This perspective raises profound questions about the nature of reality and the observer. Does reality exist independently of observation? Or does it require a conscious mind to bring it into being? These questions do not imply that human thought directly influences particles, but they suggest that the fabric of reality is intricately linked to our measurements and interpretations. It's important to highlight that this view remains highly debated among physicists. While some endorse the idea that consciousness affects quantum systems, others argue that observations can be made by any measurement device, not requiring human consciousness. Thus, the link between quantum mechanics and consciousness encourages both scientific exploration and philosophical reflection, revealing the depth and complexity of our understanding of the universe. Quantum mechanics offers a fascinating lens through which we can explore the mysteries of the universe. At its core, this branch of physics examines the behavior of particles at incredibly small scales, where the rules of the universe appear to shift dramatically. By understanding these minute building blocks of matter, scientists gain insight into the fundamental nature of reality itself. One of the key aspects of quantum mechanics is the idea of superposition, which suggests that particles can exist in multiple states at once until they are observed. This concept has opened up intriguing questions about the fabric of the universe, whether it is deterministic or inherently probabilistic. By harnessing these principles, researchers can investigate phenomena such as black holes and the early moments of the universe, where classical physics falls short. Entanglement, another cornerstone of quantum mechanics, allows particles to become interconnected in such a way that the state of one instantly influences the state of another, regardless of distance. This phenomenon hints at deeper connections within the universe, raising speculative ideas about the interconnectedness of galaxies and the very structure of spacetime. Furthermore, emerging technologies based on quantum principles, like quantum computing, could revolutionize our ability to simulate complex systems, allowing for advanced models of cosmic events and conditions. These high-powered simulations could lead to breakthroughs in our understanding of everything from the formation of stars to the behavior of dark matter. By delving into quantum mechanics, we unlock a treasure chest of possibilities. It helps us peel back the layers of reality, revealing how the universe operates at its most fundamental level and deepening our appreciation for the cosmic dance that governs all existence. Virtual particles are fascinating creations of quantum mechanics existing in the very fabric of reality. Though they cannot be directly observed, they emerge as fleeting disturbances in the energy field that permeates space. Imagine the ocean's surface, with waves continually forming and dissipating. Virtual particles behave in a similar way, popping in and out of existence over incredibly brief moments. These ephemeral entities arise due to the uncertainty principle, which dictates that energy levels can fluctuate even in a vacuum, providing a kind of wiggle that allows these particles to manifest momentarily. The presence of virtual particles significantly influences the forces that govern our universe. They contribute to processes such as the exchange of forces between particles, like how electrons in an atom interact. Picture a game of catch where each player throws a ball back and forth. In quantum terms, the exchange occurs through virtual particles acting like messenger particles, carrying forces between particles while never being directly observed. These transient phenomena also play a crucial role in defining the behavior of matter and energy at the quantum level. For instance, virtual particles are involved in phenomena like Hawking radiation, where black holes emit radiation due to the interactions of virtual particles near their event horizons. This interaction illuminates the delicate balance between reality and perception, suggesting that our universe is constantly swarming with activity beyond what we can directly perceive. Virtual particles shape our understanding of reality by underscoring the complexities and nuances of quantum mechanics, revealing a universe that is far more dynamic and interconnected than it seems. They remind us that even in the emptiest space, a vibrant tapestry of interactions is taking place, influencing the very building blocks of our existence. The idea that the universe might function as a giant quantum computer is an intriguing concept that merges physics with information theory. At its core, a quantum computer operates using principles of quantum mechanics, processing information in ways that classical computers cannot. Imagine traditional computers as sophisticated libraries, organizing and retrieving books based on a linear path. In contrast, a quantum computer resembles a vast web with interconnected pathways that allow multiple possibilities to be explored simultaneously. To envision the universe as a quantum computer, consider the fundamental building blocks of reality, such as particles and their interactions. In a quantum framework, these particles exist not in fixed states, but in a superposition of possibilities, similar to how a coin spins, embodying both heads and tails until it lands. Every interaction and event in the universe could be thought of as a computation, where the outcomes depend on the complex interplay of these quantum states. Moreover, if we perceive information itself as a crucial aspect of the universe, the entire cosmos could be viewed as a vast network of quantum bits, or qubits. Each qubit can represent a multitude of outcomes, processing and storing information in ways reflective of how the universe operates, where every event influences another, cascading through time and space. This leads to the notion that reality isn't just a series of events, but rather an intricate calculation of existence. However, while this theory captivates the imagination, it remains highly speculative. A deep understanding of how quantum mechanics relates to the workings of the cosmos is still an open area of research. The intersection of science and philosophy in this topic ignites stimulating discussions about the fundamental nature of reality and whether our universe is indeed a complex, ongoing computation that transcends our current technological capabilities. The fabric of space, often referred to as spacetime, is a fundamental concept in understanding the universe. Imagine it as a vast, flexible sheet that combines the three dimensions of space with the one dimension of time. This interconnected framework allows us to perceive not just where we are, but when we are, creating a four-dimensional experience of reality. In this model, massive objects like planets and stars create indentations or curves in the fabric of spacetime, somewhat akin to a heavy ball placed on a stretched rubber sheet. This curvature affects the movement of other objects, guiding them along curved paths. This is how gravity works. The more massive the object, the deeper the indentation it creates, resulting in a stronger gravitational pull on surrounding objects. Manipulating the fabric of spacetime has been a topic of fascination in theoretical physics. While contemporary science has yet to find practical methods for such manipulation, concepts like wormholes suggest a possibility. These theoretical structures could connect distant points in the universe, potentially allowing for faster-than-light travel. However, creating or stabilizing a wormhole would require energy forms and conditions beyond our current technological capabilities, leading to many unanswered questions regarding safety and practicality. Additionally, ideas like warp drives propose bending space-time itself around a spacecraft, theoretically making it possible to traverse great distances without breaking the laws of physics as we understand them. But again, such technology resides in the realm of speculation and advanced theoretical models. While the fabric of space is profoundly influential in shaping our universe and our understanding of gravity, efforts to manipulate it remain a complex and largely theoretical endeavor. For now, it is a captivating area of exploration, inviting further inquiry into the depths of physics and the mysteries of the cosmos. Wormholes are fascinating theoretical constructs in the realm of physics, often regarded as a shortcut through the fabric of space and time. The idea originates from the applications of Einstein's theory of relativity, which describes how mass and energy interact with spacetime. Essentially, a wormhole can be visualized as a tunnel linking two distant points in the universe, allowing for the possibility of near-instantaneous travel between them. However, while the mathematics supporting wormholes is highly intriguing, actual evidence of their existence has yet to be discovered. They remain purely hypothetical and are often portrayed in science fiction as a means to traverse vast distances or even travel through time. The challenges surrounding their existence are immense. For instance, maintaining a stable wormhole would likely require exotic matter, substances with unusual properties, such as negative energy density, which have not been conclusively proven to exist. Moreover, even if a stable wormhole could be created, traveling through it may present significant obstacles. The nature of such a journey might involve extreme gravitational forces, which could be lethal, along with various unknown physical phenomena that could arise within the wormhole itself. While wormholes ignite the imagination and are rooted in theoretical physics, they remain unproven and fraught with challenges that make them a tantalizing yet distant prospect in our quest for interstellar travel. The speed of light is often referred to as the ultimate speed limit in the universe, and this is based on principles established by the theory of relativity. To grasp this idea, consider that as an object moves faster, it requires more energy to continue accelerating. When an object approaches the speed of light, the energy needed increases dramatically, essentially reaching an insurmountable threshold. This unprecedented demand for energy means that no matter how much we apply, the object cannot cross that speed barrier. Furthermore, as an object nears the speed of light, its mass effectively increases, which further complicates the ability to accelerate. For light itself, a massless particle traveling at this maximum speed is not just a characteristic, it's essential to its existence. This relationship between mass, energy, and speed illustrates a fundamental reality of our universe. Nothing with mass can reach or exceed the speed of light. Additionally, when we think about how this speed limit plays out in the cosmos, it reveals intriguing consequences for how we perceive time and space. For example, approaching the speed of light can lead to time dilation, where time appears to slow down for the traveler compared to someone at rest. This means that journeys across vast cosmic distances might alter our understanding of time itself. While the speed of light is fundamentally a limit on how quickly information and matter can travel, it is also a doorway into exploring the nature of our universe and how intertwined speed, time, and gravity truly are. This makes the concept not only a rule of physics, but a key to understanding the very fabric of reality we inhabit. The concept of space expanding faster than light can be a bit perplexing, but it's important to distinguish between the movement of objects through space and the expansion of space itself. In our universe, nothing with mass can move through space at the speed of light. This is a fundamental rule of physics. However, the expansion of space as described by the Big Bang theory allows for distances between galaxies to increase at rates that can exceed the speed of light. Imagine you are on the surface of a balloon being inflated. As the balloon expands, points on the surface move away from each other. If you placed dots far apart on the surface before inflation began, you would see them moving away from each other as the balloon blows up. Some dots could be repositioned so far apart that the distance between them stretches faster than light could travel. This doesn't violate the laws of physics because the dots aren't moving through space. Rather, it's the fabric of spacetime itself that is expanding. In the early universe, space expanded so rapidly during a phase called cosmic inflation that it effectively pushed regions of space far apart at speeds greater than light, making it possible for the universe to reach its current vast scale. Though it's a mind-bending concept, this differentiation is key to understanding how the universe evolves and why it can expand in ways that defy our traditional notions of speed. Thus, while matter and energy may not surpass the speed of light, the cosmos can certainly expand in a way that allows for incredible distances to grow in a relatively short amount of time. Vacuum energy plays a vital role in the fabric of the cosmos, acting as a mysterious force that influences the universe's expansion. At the heart of this concept is the idea that even in empty space, there exists a form of energy that arises from the quantum fluctuations of particles. Picture a still lake. The surface may appear calm, but underneath, tiny ripples are constantly forming and disappearing. This activity represents the vacuum state, where particles can pop in and out of existence, contributing to what we call vacuum energy. This energy has profound implications for the universe. It is linked to the phenomenon of dark energy, which scientists believe is driving the accelerated expansion of the universe. Imagine the cosmos as a balloon that is being blown up more and more rapidly over time. This acceleration isn't just happening by chance. It is influenced significantly by vacuum energy. When it comes to cosmic structure, vacuum energy helps drive the development of galaxies and clusters. It creates a backdrop that can shape the gravitational environment, affecting how matter interacts and organizes over vast cosmic timescales. Essentially, vacuum energy serves as a quiet but powerful force behind the scenes, pushing the universe apart and altering its destiny. Moreover, researchers continue to explore how vacuum energy plays into fundamental questions of physics, including the nature of space and time itself. The more we learn about this enigmatic energy, the more it reveals its crucial role in shaping the large-scale structure of all that we observe, providing a deeper understanding of where we come from and where we are headed in this ever-expanding universe. Fast radio bursts are enigmatic flashes of radio waves that last for just a few milliseconds, yet they are incredibly powerful. Although scientists are still piecing together the mystery surrounding their origin, several leading theories have emerged. One prevalent idea suggests that these bursts may originate from the explosive end stages of massive stars, specifically from magnetars. Magnetars are a type of neutron star with an extraordinarily strong magnetic field. When these stars undergo a violent event, such as a starquake, they can release immense amounts of energy in the form of radio waves, leading to the brief but intense bursts we observe. Another hypothesis points to the existence of merging dense objects, such as neutron stars or black holes. When these incredibly massive bodies collide, the energy released can produce fast radio bursts. The gravitational forces and electromagnetic phenomena at play in these cataclysmic events might be responsible for the intense signals that reach us, traveling across vast cosmic distances. Some researchers also propose that more exotic celestial activities, like certain types of supernovae or even signatures from extraterrestrial civilizations, might generate these bursts. However, no definitive evidence has substantiated such theories. Each potential source underscores the complexity of our universe and highlights the many processes that can create such captivating astronomical phenomena. As technology improves and researchers collect more data, the quest to understand the origins of fast radio bursts continues, potentially unlocking secrets of the cosmos along the way. The universe holds vast expanses of darkness, but this does not mean it is devoid of celestial bodies. In fact, many stars and planets exist in regions that are difficult for us to observe. Dark areas of space often contain dust and gas, which can obscure our view of distant objects. These regions are not empty. They can harbor young stars forming in clouds of gas, or even be home to exoplanets, planets that orbit stars outside our solar system. Additionally, there are types of celestial objects that are intrinsically faint and may go unnoticed. For instance, brown dwarfs, sometimes referred to as failed stars, are objects that are too small to sustain nuclear fusion like a normal star, but too large to be considered planets. They emit very little light, making detection challenging. Similarly, rogue planets, those that do not orbit any star, float through the void of space, often escaping the clutches of a stellar system. These can be hard to find because they do not have a bright host star illuminating them. Scientists have developed advanced techniques to search for these hidden worlds. They use specialized telescopes equipped with powerful sensors that can detect the faintest sources of light. Observations in different wavelengths of light, including infrared, allow us to peer through dust clouds and discover objects that would otherwise remain obscured. While the cosmos does feature dark regions where stars and planets may seem hidden, modern astronomy is equipped to uncover their secrets, revealing a richer tapestry of the universe than we can observe with the naked eye. Quasars, short for quasi-stellar objects, are among the most luminous entities in the universe, shining with a brilliance that can outshine entire galaxies. They are powered by supermassive black holes located at the centers of distant galaxies. As material spirals into these black holes, it forms an accretion disk. Think of it as a swirling mass of gas and dust that generates immense friction and heat. This process of material falling into the black hole releases an extraordinary amount of energy, transforming it into light and other forms of electromagnetic radiation across a vast spectrum. The energy produced during this infall is what makes quasars so incredibly bright, often visible across billions of light-years of cosmic distance. Essentially, quasars can emit more energy than an entire galaxy composed of billions of stars. Their great distance from Earth, often situated billions of light-years away, means that we are looking back in time, witnessing the universe as it was when these quasars were at their peak activity. This creates the illusion of them being point-like stars, hence the name quasi-stellar. The brightness of quasars also comes from the incredible efficiency of the black hole accretion process, with a small portion of the mass being converted into energy, as described by the famous equation relating mass and energy, although we'll refrain from using the specific symbols here. Quasars are brilliant beacons of light powered by the immense gravitational energy of supermassive black holes, illuminating the depths of space and giving us insights into the early universe. Rogue planets, the celestial bodies wandering through space without a star to orbit, present a fascinating possibility when it comes to the potential for life. While we often associate the conditions for life with planets that orbit stars, where warmth and light can support biological processes, the environment on a rogue planet is markedly different and poses unique challenges. These planets can still retain heat from their formation or generate internal heat through geological activity. If a rogue planet has sufficient thermal energy, it may create subsurface oceans beneath layers of ice, much like some of the moons found in our own solar system, such as Europa and Enceladus. In such environments, the presence of liquid water is a key ingredient for life as we know it. Moreover, if there are chemical processes occurring on the ocean floor driven by geothermal energy, it's conceivable that microbial life could thrive in these dark, isolated habitats. However, the absence of sunlight presents a significant hurdle. On a rogue planet, photosynthesis, the process used by many Earth organisms to convert sunlight into energy, would be impossible. Any potential life forms would need to rely on alternative energy sources, such as chemical reactions or even radiation from distant stars if they are within a certain range. Researchers have begun to explore these intriguing ideas, examining the potential for extremophiles, life forms that flourish in extreme environments. If such organisms could survive and evolve in the harsh, frigid darkness of a rogue planet, It would challenge our definitions of habitability and where life might exist in the universe. While rogue planets may not be ideal hosts for life, they could potentially harbor life in ways that we do not yet fully understand. Each discovery adds a new layer to our knowledge of the conditions under which life might arise, pushing the boundaries of where we consider the possibility of life beyond Earth. In the vastness of the universe, the cosmic web is a grand architectural structure made up of filaments of galaxies and dark matter, interspersed with expansive regions known as voids. Picture the universe as a honeycomb. Clusters of galaxies represent the cells, while the voids are the empty spaces between them. These voids can stretch across enormous distances, often containing very few or even no galaxies at all. The formation of these voids is deeply tied to the gravitational effects of matter in the universe. After the Big Bang, tiny fluctuations in density led to regions where matter began to clump together due to gravity. Over billions of years, these denser regions attracted more matter, forming galaxies and clusters, while the lower density areas fell behind, leading to the emptiness we observe as voids today. Additionally, dark matter plays a crucial role. Although it doesn't emit light, it forms a framework that influences the distribution of regular matter. The gravitational pull of dark matter enhances the formation of filaments, while simultaneously leaving vast spaces underpopulated. The dynamics of expansion also contribute significantly to these voids. As the universe expands, the less dense regions, those that became voids, expand more quickly than denser regions. This expansion rate causes these voids to grow over time, further increasing the distances between the galaxies clustered along the filaments. Therefore, these great voids serve as reminders of the complexities and intricacies of cosmic evolution, where the interplay between gravity, density fluctuations, dark matter, and the expansion of space has shaped the remarkable structure of our universe. Each void, despite its emptiness, is part of a system that contains a rich narrative of cosmic history. The four fundamental forces of the universe: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, are the cornerstones of our understanding of physical interactions. However, the universe is vast and complex, leading scientists to consider the possibility of unknown forces beyond these established interactions. One of the primary reasons we explore these unknown potentials is the observation that ordinary matter, which constitutes stars, planets, and even us, only accounts for a fraction of the universe's total mass-energy content. The mysterious components, called dark matter and dark energy, suggest that there are forces or effects we have yet to fully comprehend. Dark matter, for instance, does not emit light or energy, making it invisible to our current detection methods. Yet, it exerts a gravitational influence affecting the motion of galaxies and galaxy clusters. This indicates there might be additional forces at play, influencing the behavior of this unseen mass. Similarly, dark energy drives the accelerated expansion of the universe. This phenomenon challenges our understanding of gravity as it pushes galaxies apart, suggesting an energy field that we have yet to identify. Moreover, various theories in physics propose additional forces that could exist, such as those from string theory or concepts involving extra dimensions. These theories attempt to unify the fundamental forces and suggest that what we perceive might just be aspects of a more profound underlying reality. While the four fundamental forces form the basis of our current scientific framework, the search for unknown forces prompts further exploration. It encourages scientists to push the boundaries of our understanding, continually questioning what lies beyond our established knowledge. The universe remains full of mysteries, and with each discovery, new questions inevitably arise, guiding us deeper into the exploration of the cosmos. Uniting quantum mechanics with general relativity represents one of the most significant challenges in modern physics. To understand why this is so complex, consider how each of these theories describes different aspects of our universe. Quantum mechanics excels at explaining the behavior of the very small, like atoms and subatomic particles, where uncertainty and probabilities dominate. In stark contrast, general relativity describes the cosmos on a grand scale, focusing on the forces of gravity and how massive objects like planets and stars warp the fabric of space and time. The tension arises because these two frameworks operate under fundamentally different rules. In quantum mechanics, particles can exist in multiple states simultaneously, while in general relativity, gravity is a smooth, continuous field. When trying to merge the unpredictability of the quantum world with the structured universe defined by general relativity, scientists encounter contradictions and paradoxes. A potential path toward unification involves theories like string theory, which suggests that the fundamental building blocks of the universe are tiny, vibrating strings rather than point-like particles. These theories aspire to create a single framework that can describe all fundamental forces, including gravity, in a quantum context. Another approach is loop quantum gravity, which attempts to quantize space-time itself, suggesting a granular structure to space-time at the smallest scales. While these theoretical developments are promising and inspire hope for a deeper understanding of the universe, no experimental evidence currently confirms any of these unifying theories. Thus, while physicists continue to grapple with these profound questions, the quest to unify quantum mechanics with general relativity remains an open frontier, inviting both scientific rigor and imaginative exploration. Such a unification could revolutionize our understanding of the cosmos, shedding light on the very fabric of reality. Yes, certain particles and forces become prominent or even exclusively exist in extreme environments, such as those found in the core of stars or during high-energy cosmic events. One of the most remarkable examples is found with neutrinos. These nearly massless particles are produced in great quantities during stellar processes like nuclear fusion or during explosive events such as supernovae. In regular circumstances on Earth, they are incredibly elusive and can pass through matter virtually undetected. However, in the intense environments of stars, they flourish. Additionally, consider the concept of quark-gluon plasma. Under incredible temperatures and energy levels, such as those that existed just after the Big Bang, quarks and gluons, the fundamental constituents of protons and neutrons, could exist freely instead of being locked within atomic structures. This state of matter can be temporarily recreated in high-energy particle collisions, such as those conducted in particle accelerators. The forces that govern these particles can also act differently in extreme scenarios. For example, gravity becomes immensely powerful in the vicinity of black holes, reshaping the fabric of space-time itself. This shows that while fundamental forces remain consistent, their effects can change dramatically based on the extreme conditions surrounding them, leading to phenomena that are otherwise unobservable in normal situations. Extreme environments not only catalyze the existence of unique particles, but also allow us to glimpse the nuances of the forces that govern our universe. Each of these scenarios enriches our understanding of physics and the fundamental workings of nature, providing insights that shape our comprehension of the cosmos. String theory presents a fascinating framework that suggests the very building blocks of the universe are not just tiny particles, but rather one-dimensional objects called strings. Picture these strings vibrating at different frequencies, much like how different musical notes emerge from a guitar string. The unique ways in which these strings vibrate could give rise to the diverse particles we observe, such as electrons or quarks. This revolutionary idea attempts to unify the two great pillars of modern physics: general relativity, which explains gravity and the structure of space-time, and quantum mechanics, which governs the behavior of the tiniest particles. The allure of string theory lies in its ambition to provide a comprehensive theory that encompasses all fundamental forces and forms of matter, an idea often referred to as a theory of everything. However, string theory is highly complex and remains largely hypothetical, as it requires a number of additional dimensions beyond the familiar 3 dimensions of space and 1 of time. Some versions propose as many as 10 or 11 dimensions. These extra dimensions are thought to be compact and hidden from our everyday experience. Despite its potential, string theory has yet to provide testable predictions that can be observed through experiments. This lack of empirical evidence raises questions about its validity as an ultimate explanation. The quest for understanding the universe is ongoing, with physicists exploring various other theories alongside string theory. Until conclusive evidence can support one framework over another, the mystery of the universe remains tantalizingly unsolved, promising to keep researchers and enthusiasts alike engaged for many years to come. A theory of everything is an ambitious concept in physics aimed at unifying all fundamental forces and particles in a single framework. Imagine standing in a vast library filled with books, each documenting different aspects of the universe, from the tiniest particles to the grand forces that govern celestial motion. Up until now, these are treated separately. Gravity is described by one set of principles, while electromagnetic, weak and strong nuclear forces are understood through another. A comprehensive theory would seek to weave all these narratives into one coherent story. This might involve a deeper understanding of the underlying structures of reality, where particles are not merely points, but can be understood as vibrations of more fundamental strings. Picture musical notes playing together. When perfectly harmonized, they create a symphony that represents the universe's fabric. This theory would likely incorporate complex mathematical structures, but at its heart would have to speak to the fundamental unity of physical interactions. It could provide explanations for phenomena like gravity at a quantum level and explore how forces interact under extreme conditions, such as in black holes or during the moments after the Big Bang. While currently elusive, such a theory would illuminate the connections between the different forces, suggesting that they are merely different manifestations of a single underlying reality. By grasping this unified standpoint, humanity could ultimately not only better understand the universe, but also anticipate the laws governing future discoveries, some of which might challenge everything we think we know. This quest for a theory of everything captures the imagination, reflecting our drive to uncover the mysteries of existence itself. The universe is currently on an unstoppable course of expansion. Imagine blowing up a balloon. As air fills it, every point on the surface moves farther away from each other. Similarly, galaxies are receding from one another, driven by an unseen force known as dark energy. This energy accounts for a significant portion of the universe's makeup and appears to have a repulsive effect, pushing galaxies apart. Scientists grapple with questions about the future of this expansion. Several theories exist, and which one holds true is still under investigation. One possibility is that the universe will continue expanding indefinitely. In this scenario, galaxies would slowly drift away from each other, leading to a cold and sparse cosmos where stars eventually burn out and galaxies fade from view. Alternatively, there is the notion of a slowing expansion, where the force of gravity could eventually overcome dark energy, bringing galaxies closer together over enormous timescales. This scenario might lead to a cosmological event termed the Big Crunch, where the universe collapses back in on itself. Another intriguing idea is the potential for a fluctuating expansion, where the universe might expand and contract periodically. Each cycle could lead to different evolutionary paths for cosmic structures. At this stage, while evidence strongly supports the acceleration of the universe's expansion, the ultimate fate remains a profound mystery yet to be answered. Scientists continue to gather data and develop models to better understand the complex interplay of forces shaping our universe, a journey that reveals more about the nature of reality itself. To understand the possibility of a big crunch, we first consider how the universe is currently expanding. This expansion, first discovered in the early 20th century, suggests that galaxies are moving away from one another, akin to spots on a rising balloon. If the universe's expansion were to slow down significantly, it could eventually reverse. In the scenario of a big crunch, the gravitational forces among all matter in the universe would take over. Imagine the universe as a colossal balloon that starts to deflate. Instead of inflating further, the balloon begins to collapse inwards. All galaxies and celestial bodies would be drawn closer together until they reconvene at a single point. However, the fate of the universe hinges on its overall density, the amount of matter relative to the space it occupies. If this density is high enough, gravity could slow the expansion, stop it, and initiate a collapse. Conversely, if the universe's density is low, the expansion might continue indefinitely, leading to a scenario called the Big Freeze, where galaxies drift apart forever, ultimately leading to a dark and cold cosmic future. Current observations suggest that the universe is not just expanding, but that this expansion is accelerating, likely due to an unknown force termed dark energy. This acceleration raises questions about whether a big crunch could ever occur, as the push of dark energy seems to dominate and push galaxies further apart. In conclusion, while the Big Crunch is a fascinating idea, current evidence leans toward an expanding universe with no impending collapse. The interplay of forces in the universe remains a central mystery, making any definitive fate of the cosmos an open question in the grand tapestry of spacetime. When all stars burn out, the universe will enter a new phase known as the Dark Age. Initially, stars shine brightly, illuminating the cosmos with their light, creating galaxies that shimmer like jewels. However, over astronomical timescales, these stars exhaust their nuclear fuel, leading to their eventual death. As massive stars deplete their resources, they explode in brilliant supernovae, leaving behind remnants like neutron stars or black holes. Smaller stars, which make up the majority, will simply fade away over billions of years, extinguishing their light gradually. Once the last star flickers out, the night sky will transform into a vast expanse of darkness. Silence will reign in a universe once filled with vibrant stellar activity. In this lifeless universe, the remnants of stars will linger. There will be white dwarfs, remnants of middleweight stars, cooling over eons without the processes that gave them life. Black holes will exist scattered about, their strong gravitational pull remaining as a haunting reminder of once mighty stars. The leftover gas and dust might coalesce over enormous timescales, forming new cosmic structures, though without the ignition of stars, the universe's capacity for dynamic change will be severely limited. This cold, dark universe will highlight the inevitability of change and decay on a cosmic scale. Eventually, even these star remnants will themselves be subject to decay. Over immense timescales, black holes can evaporate through a process known as Hawking radiation, releasing a faint glow as they slowly lose mass and energy. Ultimately, without stars to create the conditions necessary for life or the energy to drive physical processes, the universe will slowly drift towards an unimaginable quietude, a vast void marked only by the remnants of its once glorious past. This scenario invites reflection on the transient nature of existence on both cosmic and human scales, reminding us of the life cycle of stars and the ever-evolving universe. The concept of reversing entropy is a fascinating one, rooted in the second law of thermodynamics, which states that the total entropy of an isolated system always tends to increase over time. Entropy, often associated with disorder, is like a measure of how energy is distributed. Think of it this way. In a room filled with air, if you suddenly release a perfume, it will spread throughout the room, increasing the disorder until it is evenly mixed. Reversing this process, where the perfume molecules spontaneously gather back into the bottle, would imply a decrease in entropy. In practical terms, reversing entropy on a system-wide scale seems virtually impossible due to natural laws. However, in localized systems, such as in living organisms or engineered processes, it is entirely feasible to create pockets of lower entropy. For example, while a plant decreases its local entropy by turning sunlight into energy and growing, the overall entropy of the universe still increases as energy is expended in the process. There are theoretical discussions around concepts like quantum mechanics and the universe itself, which might suggest some scenarios where entropy could be manipulated or act differently in certain conditions. For instance, some researchers speculate about the behavior of black holes and their entropy, proposing that at the event horizon, different rules might apply. But these remain speculative and not practical for real-world applications. Ultimately, while we can certainly generate order in certain environments, the overarching trend in the universe is a movement towards higher entropy. Hence, in the grand scope of things, the idea of truly reversing entropy on a cosmic level remains outside our current scientific understanding and technological capabilities. The universe seems inherently designed to embrace an ever-increasing complexity and disorder. The idea of intelligent life extending the lifespan of the universe sparks fascinating considerations about our role in the cosmos. To understand this, we first need to look at the universe's natural progression. The universe is governed by fundamental laws of physics that lead to phenomena like the eventual cooling of stars, the gradual spread of galaxies, and the potential for a scenario known as the heat death, where the universe reaches a state of maximum entropy. Now, intelligent life, especially advanced civilizations, could theoretically influence local environments. For instance, they might develop technologies that utilize energy in unprecedented ways. Harnessing the energy of stars could mean using massive solar collectors to capture and store sunlight in an efficient manner. This manipulation of energy sources could allow for longer-lasting civilizations or even the ability to move to more energy-rich environments, such as different star systems. However, extending the universe's lifespan on a cosmic scale is far more complex. This would require actions on a scale that is currently beyond our understanding. For example, if civilizations successfully harness dark energy, the force believed to be accelerating the universe's expansion, they may manipulate cosmic expansion in a way that prolongs energy availability. But such projects involve challenges that we cannot yet fully grasp. Moreover, any significant intervention would need to be sustainable. The pursuit of extending life at a local level does not necessarily equate to changing the fundamental fate of the universe. Even with advanced technology, limitations imposed by the laws of thermodynamics and cosmic scale would still act as formidable constraints. In conclusion, while intelligent life could potentially alter their local environment and extend their own existence in fascinating ways, influencing the ultimate fate of the universe presents grand challenges. The interplay between civilization and cosmic evolution remains an exhilarating question, blending the realms of science and philosophical speculation about our place in this vast expanse. The origin of life on Earth is a fascinating journey that begins billions of years ago, when our planet was a very different place. Imagine a young Earth shrouded in molten rock and volcanic activity, with a chaotic atmosphere filled with gases. As the planet began to cool, water vapor condensed, forming oceans. These primordial oceans became a crucible for the first building blocks of life. Scientists suggest that life started with simple organic molecules, possibly formed through chemical reactions in the atmosphere or delivered by meteorites. Over time, these molecules began to combine in complex ways, leading to the creation of larger structures such as proteins, sugars, and nucleic acids, the essential components of living systems. One key concept in understanding this process is the idea of self-replication. Some of these early molecules were able to make copies of themselves. This ability to reproduce is a hallmark of life as we know it. Through billions of years of random changes in these molecular structures, known as mutations, some variants proved more successful at surviving and replicating in their environments. As conditions continued to evolve, these primitive life forms, likely consisting of simple cells, began to harness energy from their surroundings. This marks a significant turning point, the emergence of biological processes that allowed living organisms to grow, reproduce, and adapt. Eventually, some of these simple cells developed the ability to photosynthesize, converting sunlight into energy and releasing oxygen into the atmosphere. This oxygenation event drastically transformed the planet, paving the way for more complex life forms to evolve, ultimately leading to the rich diversity of life we see today. Although the exact pathway remains a subject of research, it highlights the incredible journey of how non-living compounds transitioned into the intricate web of life that thrives on Earth. Humanity's connection to the universe is profound and multifaceted, extending far beyond our immediate comprehension. As we gaze at the stars, we recognize that the very elements that make up our bodies, such as carbon and oxygen, originated in the hearts of ancient stars that exploded long ago, scattering their remnants across the cosmos. This cosmic recycling means that, in a literal sense, we are made from stardust, binding us to the universe at a fundamental level. Yet, our connection encompasses more than just physical elements. The universe operates under laws of physics and patterns that govern everything from the orbits of planets to the formation of galaxies. Many of these principles remain partly understood, leaving tantalizing hints of deeper connections yet to be discovered. For instance, concepts like dark matter and dark energy shape the cosmos in ways that challenge our understanding. They influence the structure and expansion of the universe, yet their nature remains largely enigmatic, suggesting that other dimensions of reality might connect us to the cosmos. Moreover, our consciousness raises intriguing questions about the universe's fabric. The way we perceive space, time, and existence might be intertwined with universal phenomena in ways we have yet to fully understand. Some scientists explore the idea that consciousness itself could play a role in shaping reality, bridging the gap between the observer and the observed. This opens the door to philosophical debates about the nature of existence and our place within it. As we continue to explore the universe, each discovery acts as a thread that weaves us deeper into the cosmic tapestry. With every new insight, we not only expand our knowledge, but also reinforce the idea that we are all part of a larger whole. The mysteries that still elude our grasp serve as reminders that our connection to the universe is likely richer and more intricate than we can currently imagine. The journey of learning never ends. It merely evolves as we delve further into the wonders surrounding us. The dream of humanity spreading across the stars is both a tantalizing vision and a profound challenge. While the vastness of the universe can feel intimidating, the pursuit of interstellar travel is grounded in science and human ingenuity. Imagine our solar system as a small neighborhood within a sprawling city. Today, we have already ventured to other planets, sending robotic explorers to gather valuable information about their environments. To reach beyond our solar system, we need to overcome significant obstacles. First and foremost is the immense distance. Even the closest star systems are light years away, which means that even at the speed of our current spacecraft, a journey could take thousands of years. However, researchers are exploring concepts that might one day enable faster travel, such as the idea of utilizing incredibly powerful propulsion systems, including those that could harness nuclear energy or even utilize the surrounding cosmic environment, like solar sails propelled by light. Moreover, the challenge goes beyond mere travel. For humanity to survive away from Earth, we need sustainable living conditions. This means developing habitats that can provide food, water, and air. Scientists envision self-sufficient colonies on Mars or moons, such as Europa, which could potentially harbor subsurface oceans. These stepping stones would create the technological and social frameworks necessary for longer journeys. Then there's the question of human adaptation. Space travel might require genetic or technological enhancements to help people thrive in environments with different gravitational fields, radiation levels, and atmospheric compositions. We would need to prepare not just for the travel itself, but for the life that continues afterward. While we may be far from journeying across the stars today, advancements in technology and our relentless curiosity drive the vision. Each step we take in space exploration lays the groundwork for the possibility that one day humanity could truly become a multi-world species, exploring distant planets and perhaps forging connections in the cosmic tapestry of the universe. Such an endeavor would reshape our understanding of life and our place in the cosmos. Humanity plays a pivotal role in unraveling the mysteries of the universe through curiosity, observation, and innovation. From the very beginning, our species has gazed up at the night sky, wondering about the stars and the endless expanses beyond our planet. This innate desire to explore and comprehend the cosmos has driven advancements in technology, science, and philosophy. Observational tools like telescopes have transformed our understanding. Just a few centuries ago, the ability to see distant celestial bodies was limited. With each technological leap, we have peeked further into the cosmos. These instruments allow us to study everything from the faint glow of remote galaxies to the intricate dance of planets within our solar system, revealing the universe's vastness and complexity. The accomplishments of humanity in space exploration have brought extraordinary insights. Manned missions to the Moon, robotic explorers on Mars, and observatories stationed beyond our atmosphere have expanded our knowledge base dramatically. Each mission contributes to a tapestry of data that scientists analyze, helping us understand not just our own planet, but also the processes that govern celestial bodies and cosmic phenomena. Moreover, the pursuit of answers to profound questions about existence reflects our ongoing quest to grasp fundamental truths. Are we alone in the universe? What is the nature of dark matter and dark energy? Such inquiries lead to collaborative efforts among scientists worldwide, emphasizing that our quest for knowledge is a shared human endeavor. In addition to exploring the universe through technology and research, humanity's greatest asset may lie in its capacity for imagination. Theories of black holes, the nature of time, and the possibilities of extraterrestrial life resonate not just within the realms of science, but permeate our cultures and stories, driving further inquiry and exploration. As we strive to understand the universe's complexities, we recognize that our unique perspectives and innovative minds will continue to illuminate the grand narrative of cosmic existence. The Kardashev scale is a theoretical framework used to classify civilizations based on their energy consumption and capabilities. A Type 3 civilization harnesses the energy output of an entire galaxy, which is profoundly beyond our current technological reach. To grasp the scale, think of Type 1 as a civilization that utilizes all the energy available on its home planet, Type 2 utilizing energy on the scale of an entire star, and Type 3 operating at the galactic level. Reaching Type 3 would require advancements that we can barely imagine today. Current technologies focus on limited planetary and solar resources, and transforming that basic capacity into something that could manipulate energy from every star in our galaxy is a monumental leap. It would demand not only extraordinary technological advancements, but also a sustained commitment to cooperation among a sophisticated global or even interstellar society. Several challenges would need to be addressed, such as mastering large-scale space engineering, possibly creating megastructures around stars, and developing technologies to transport and harness energy efficiently across vast distances. This transformation could take centuries, if not millennia, and would likely require overcoming existential threats to both civilization and planet. While contemplating our future, it's essential to balance optimism regarding our potential with realism about the obstacles we face. Technological revolutions could reshape our capabilities, and environmental stewardship will determine our survival in the long run. It's uncertain whether we will reach the monumental status of a Type 3 civilization, but the idea inspires the quest for knowledge and the exploration of the cosmos, driving innovation and uniting efforts towards a shared destiny among the stars. The edge of the universe is a complex concept, primarily because the universe is expanding. Imagine the universe as a vast balloon that has been blown up. As it expands, the surface stretches and points move away from each other. When we gaze into space, we're looking back in time, seeing light from stars and galaxies that has taken a long journey to reach us. Currently, the farthest distances we can see with our telescopes are limited by how far light has traveled since the beginning of the universe. This means our view is constrained by the age of the universe itself. We can glimpse phenomena that are billions of years old, but the light from the very edge, or what might be considered the edge, of the universe hasn't had the chance to reach us yet. Building a telescope capable of seeing what could be viewed as the ultimate edge is not just a matter of enlarging our instruments. It would require overcoming the fundamental limitations imposed by light travel and the universe's ongoing expansion. Scientists are exploring different methods, including observing various wavelengths of light and utilizing technology to enhance our current telescopes, but the vast distances and the speed limit imposed by light create inherent challenges. Moreover, as we advance our understanding of the universe's structure through techniques like analyzing cosmic background radiation, we're constantly refining our idea of what the edge actually is. The universe might be infinite, or it may have boundaries shaped by its expansion history. Therefore, while we strive to make ever more advanced telescopes, capturing a complete and clear view of the universe's edge remains a tantalizing dream wrapped in the mysteries of space and time. Detecting signals from alien life is one of the greatest challenges in modern science. To uncover even the faintest whispers from an extraterrestrial civilization, scientists combine a variety of sophisticated methods and technologies. One primary approach is the use of radio telescopes. These highly sensitive instruments can pick up radio waves emitted from distant sources in space. The idea is that if an alien civilization were to send out radio signals, these telescopes could potentially capture them, much like a giant ear listening for the faintest sound in a busy crowd. But the quest doesn't stop at simply listening for alien broadcasts. Researchers also analyze various types of wavelengths, including infrared and optical light, which might indicate advanced technology. For instance, if a star system were home to an industrial civilization, it may emit unusual heat signatures or artificial light patterns that could hint at its presence. By scanning the night sky with instruments designed to detect these anomalies, scientists hope to uncover clues about extraterrestrial technologies. In addition, astronomers are turning to methods like astrobiology, which focuses on finding planets in the so-called habitable zone, areas around stars where conditions might support life. By studying exoplanets using space telescopes, scientists can analyze their atmospheres for signs of gases that might be produced by life, such as oxygen or methane. Moreover, the concept of technosignatures has gained traction. This refers to any evidence of technology that might betray the existence of intelligent life. Whether it's a pattern of light around a star indicating massive structures or peculiar emissions from celestial bodies, each discovery adds a piece to the puzzle. All of these efforts require collaboration among scientists across various disciplines, blending astronomy, biology, and technology. The search for alien life calls for both sophisticated technology and the imagination to recognize what such signals might look like. It's an ongoing quest, a race through the cosmos for the tiniest hints of life among the stars, and who knows what we might find next. Quantum computing holds incredible potential for unraveling the mysteries of the cosmos. Traditional computers process information in binary terms, using bits that represent either a 0 or a 1. In contrast, quantum computers utilize quantum bits, or qubits, which can exist in multiple states simultaneously. This unique characteristic allows quantum computers to perform complex calculations at speeds that would be impossible for conventional computers. One of the key areas where quantum computing could make a significant impact is in simulating quantum systems, which are pivotal in understanding phenomena like black holes, particle physics, and the fundamental forces of nature. For instance, modeling the behavior of particles at subatomic scales involves complex interactions that can be computationally intensive. With quantum computing, researchers could simulate these interactions more accurately and efficiently, leading to deeper insights into the fundamental workings of the universe. Additionally, quantum algorithms are well suited for tasks such as optimizing and analyzing vast amounts of data. This capability could revolutionize fields such as astrophysics, where massive datasets from telescopes and satellites require sophisticated analysis. Discovering patterns and anomalies within this data could potentially lead to new discoveries about the formation of galaxies, the nature of dark matter, or even the origins of the universe itself. Moreover, quantum computing may also assist in solving highly complex equations that describe the fabric of spacetime and the behavior of gravity at quantum levels, areas where current understanding is often limited. By tackling these equations with unprecedented speed and accuracy, quantum computers could illuminate phenomena such as the behavior of matter near black holes or the conditions present during the Big Bang. While we are still in the early stages of quantum computing development, its ability to process information in fundamentally different ways offers a promising avenue for scientists eager to explore and understand the cosmos more fully. As research continues and technology advances, quantum computing could indeed unlock new secrets of the universe, paving the way for revolutionary discoveries that challenge our current perspectives on everything from fundamental particles to the very nature of reality itself. The concept of traveling faster than light has intrigued scientists and science fiction enthusiasts alike. While traditional physics, guided by Einstein's theory of relativity, tells us that nothing can exceed light's speed, a fundamental limit, we're only beginning to explore theoretical pathways that might allow such travel. One prominent idea revolves around warp drives. Picture space as a fabric that can be warped and stretched. A warp drive would theoretically contract space ahead of a spacecraft while expanding it behind, creating a bubble that moves the ship faster than light relative to its surroundings. This means the ship itself isn't breaking light speed. Instead, it's bending the space around it to get from point A to point B in a fraction of the time it ordinarily would take. Another possibility lies with wormholes, which, as mentioned earlier, can be viewed as shortcuts through spacetime. Think of them as tunnels that connect two distant points in the universe, allowing for near instantaneous travel. Although the existence of naturally occurring wormholes hasn't been confirmed, scientists speculate that if we could stabilize and manipulate them, they might enable us to traverse vast distances in a blink. Additionally, some researchers are investigating the concept of quantum tunneling, where particles can occasionally jump between points through seemingly impossible gaps due to the quirks of quantum mechanics. While this phenomenon operates on a microscopic scale, it suggests there could be underlying principles that might someday scale up to macroscopic technologies. To turn these theories into reality, we face immense challenges. Creating and maintaining the energy required for warp drives, finding or crafting stable wormholes, or understanding quantum phenomena in the context of larger objects are monumental tasks. Nevertheless, these ideas inspire ongoing research and imagination about what the future of space travel could hold, hinting at realms that extend far beyond our current capabilities. Artificial intelligence is becoming an invaluable tool in the quest to understand the universe's deepest mysteries. Imagine AI as a powerful assistant that sifts through vast amounts of data much faster than any human could. Scientists in fields like astronomy and astrophysics generate enormous amounts of information, whether from telescopes capturing light from distant galaxies or satellites monitoring subtle changes in cosmic radiation. AI can analyze this data to identify patterns and insights that might be overlooked by the human eye. For instance, it can detect subtle signals from the cosmos, such as the faint echoes of gravitational waves created by colliding black holes, or identify exoplanets by recognizing tiny dips in starlight caused by these planets passing in front of their host stars. Moreover, AI's ability to simulate complex scenarios can enhance our understanding of theoretical concepts, like the behavior of dark matter and the evolution of the universe. By creating models that take into account countless variables, AI can help predict cosmic phenomena and test different hypotheses, revealing outcomes we might not have even considered. Additionally, by automating the discovery process and refining existing theories, artificial intelligence can accelerate the pace of scientific exploration, allowing researchers to focus on interpreting discoveries rather than getting bogged down by the sheer volume of data. Ultimately, this partnership between human intellect and machine processing power is lighting the way toward unraveling some of the most intricate questions about our universe, from the nature of black holes to the origins of cosmic structure. Ancient starlight offers a fascinating glimpse into the history of the universe. Every time we look up at the night sky, we are peering back in time. Light from distant stars and galaxies takes years, sometimes millions of years, to reach us. This means the light we observe today reveals information about the universe as it was in the past. By analyzing this starlight, scientists can uncover details about the composition of stars, the formation of galaxies, and the chemical evolution of the universe. Different elements produce unique fingerprints in the light they emit or absorb. When we study these patterns, we identify the types of elements present in a star or galaxy, tracing back the origins of those materials to the moment they formed. Moreover, ancient starlight provides context for the expansion of the universe. The way light shifts in wavelength, known as redshift, can indicate how fast a star or galaxy is moving away from us. This movement reveals critical information about the rate of expansion and aids in understanding phenomena such as dark matter and dark energy, which are fundamental to our grasp of cosmic structure. Additionally, some light we detect might originate from supernovae, the explosive deaths of stars. These specific events not only enrich the universe with heavy elements, but also serve as markers for cosmic distances, acting as a cosmic yardstick that helps us measure the universe's vastness. Ancient starlight acts as a time capsule, providing valuable evidence of the universe's history, its dynamic processes, and the intricate web of matter and energy that has shaped everything we see today. Each sparkle in the night sky tells a story that scientists continue to decode, further illuminating our understanding of existence. The vastness of the universe is filled with mysteries, and it's quite possible that we have indeed overlooked some cosmic phenomena. As we explore the cosmos, we frequently encounter new and unexpected events. One such phenomenon is dark matter, an invisible substance that affects the motion of galaxies and clusters of galaxies. While we know it exists because of its gravitational influence, its exact nature remains one of the biggest puzzles in modern astrophysics. Another area of intrigue lies within gravitational waves. First detected in 2015, these ripples in spacetime, created by colossal celestial events such as colliding black holes or neutron stars, provide a new way of observing the universe. Yet, the full range of events that might emit gravitational waves is still being uncovered, suggesting the presence of even more exotic phenomena we have yet to detect. Additionally, the concept of fast radio bursts has taken the astronomical community by storm. These brief but intense bursts of radio waves originate from distant galaxies, and while we have made some progress in understanding them, their source is still unclear. These mysterious signals challenge our current knowledge and may hint at previously unknown astrophysical processes. Satellite data and telescopes continue to reveal new cosmic events, pointing to the possibility of phenomena such as rogue black holes or exotic types of star systems that do not fit neatly into our existing frameworks. Moreover, with advancements in technology and methods, we are continually refining our tools to examine the universe more closely, leading us to consider that many phenomena might exist just beyond our current understanding. Each discovery opens up more questions, suggesting that the cosmos is brimming with enigmas waiting for the curious and patient observer. The evolution of the universe is a complex interplay of events, conditions, and interactions that span billions of years. To consider whether it could have evolved differently, we can think about several pivotal moments. Imagine the Big Bang, the very beginning of everything, as a massive explosion of energy and matter. If the initial conditions of this explosion had varied slightly, perhaps in temperature or density, the universe could have expanded in ways we can't fully predict. After the Big Bang, the formation of stars and galaxies followed. These processes were influenced by gravity, which drew matter together. If some stars had formed differently, or if supernovae, explosive deaths of massive stars, had occurred at different times or in different places, the distribution of elements essential for life could have changed dramatically. These elements, forged in the hearts of stars, are the building blocks of planets and eventually life itself. Another crucial event was the formation of our solar system. The precise alignment and interactions of celestial bodies ultimately shaped our planet's environment. If the Earth had formed a little closer to the Sun, or if the Moon had not stabilized our tilt and rotation, our climate could have been vastly different, possibly inhibiting the emergence of life as we know it. Evolution includes not just cosmic events, but also biological milestones. Every major extinction altered life's trajectory. Consider the asteroid impact that led to the extinction of the dinosaurs. If this cataclysm had not occurred, mammals may not have had the opportunity to thrive, leading to a vastly different ecological landscape today. The universe's evolution is deeply interconnected with countless historical events. Each moment, whether cosmic or biological, contributes to the delicate tapestry of existence. In a different version of this history, we might inhabit a universe where different forms of life prevail, perhaps even intelligent beings quite unlike ourselves. The possibilities are as boundless as the universe itself. Recent discoveries in the cosmos are paving the way for a new understanding of our universe, with implications that could revolutionize not just astronomy, but our very place within this grand expanse. One of the most exciting areas of research is the study of dark matter and dark energy. Scientists suspect that these mysterious components make up a significant portion of the universe, affecting how galaxies form and evolve. Unraveling their nature could change our fundamental grasp of physics and the cosmos's structure. Another breakthrough is the visualization of exoplanets, planets orbiting stars outside our solar system. With advances in technology, astronomers are now able to analyze the atmospheres of these distant worlds. This could potentially lead to the discovery of Earth-like conditions beyond our planet, igniting hope in the search for extraterrestrial life. Understanding the unique environments of these exoplanets could shed light on the origins of life itself. Additionally, observations of gravitational waves have opened a new window into the universe. These ripples in spacetime, caused by the collision of massive objects like black holes, offer profound insights into cosmic events that were previously invisible to traditional telescopes. This new frontier allows astronomers to track the formation and behavior of such phenomena, deepening our understanding of their impact on the surrounding universe. Finally, the ongoing exploration of our own solar system, particularly the icy moons of Jupiter and Saturn, is also revealing surprising insights. Some of these moons possess subsurface oceans that may harbor life. The study of these unique environments could redefine our concepts of habitability and challenge our understanding of how life can exist in extreme conditions. As we continue to unveil the secrets of the cosmos, these discoveries could not only reshape our scientific principles, but also spark a deeper philosophical reflection on humanity's role in the universe, ultimately altering our perception of existence itself. In the quest for knowledge, particularly in areas as vast and complex as space exploration, preparation for the unexpected is vital. First, it begins with fostering a mindset open to discovery. Scientists and researchers must be willing to embrace uncertainty, acknowledging that every mission could reveal something unforeseen. This willingness allows them to adapt their approach as new information arises. Having robust strategies in place is also essential. This includes developing flexible plans that can evolve based on real-time data. For instance, when operating spacecraft or rovers, teams often design multiple scenarios, enabling them to switch courses quickly if conditions change. Imagine sailing a ship. If the weather shifts suddenly, the captain must navigate those changes without losing sight of the destination. Furthermore, collaboration plays a pivotal role. When diverse teams come together, each bringing unique perspectives and expertise, they enhance the ability to tackle unexpected challenges. This synergy allows for innovative problem-solving, akin to assembling a puzzle where each piece contributes to a clearer picture. Additionally, looking at historical missions provides insights into potential surprises. By learning from past experiences, both successes and failures, scientists can anticipate challenges and develop contingencies. Finally, incorporating technology can significantly aid in preparation. Advanced simulations and predictive modeling help teams visualize various possibilities, equipping them with the knowledge to respond effectively. Preparing for the unexpected in our search for answers combines an open mindset, adaptability, collaboration, lessons from the past, and cutting-edge technology. This holistic approach not only strengthens our capacity to confront challenges, but also enhances our ability to uncover the mysteries of the cosmos. The question of why the universe exists is one of the most profound mysteries in science and philosophy. To explore the concept, let's start with the beginning. Scientists believe that the universe began with the Big Bang, a colossal explosion that marked the birth of space, time, and all matter. However, that initial moment doesn't inherently explain the reason behind the universe's existence. One prevailing idea is that the universe may have emerged from a quantum fluctuation, which can be thought of as a brief disturbance in a seemingly empty space filled with energy. Imagine a calm ocean where, at random moments, bubbles rise to the surface without any apparent cause. In this analogy, such fluctuations could give rise to entire worlds, suggesting that creation might be inherent in the fabric of reality. Moreover, various cosmological theories raise intriguing possibilities. Some propose that our universe is just one of many in a vast multiverse, where countless variations exist, each with differing laws of physics. In this context, our universe might simply be one of the versions that allowed for the conditions necessary for galaxies, stars, and life to emerge. Philosophically, the question dives even deeper. Why is there something rather than nothing? Some thinkers argue that existence may not require a reason at all, whereas others believe that the search for meaning lies at the core of human consciousness. Ultimately, the existence of the universe intertwines with both scientific inquiry and existential pondering, leaving us to explore not just how it came to be, but what that existence means for us and our understanding of reality. While answers may elude us for now, the journey to uncover them fuels the curiosity that drives humanity forward. The idea that our universe might be a simulation is more than just a fascinating concept. It raises profound questions about reality itself. Imagine we exist within a vast computer program akin to a sophisticated video game where everything, from the stars to our everyday lives, is the result of complex algorithms and code. This notion, popularized by philosophers and scientists alike, suggests that an advanced civilization may have the technology to create simulated worlds that could be indistinguishable from actual reality. To understand this hypothesis, consider how easily we are already blurring the lines between digital and physical experiences. Virtual reality allows us to immerse ourselves in environments that feel real, challenging our perception of existence. Now, extrapolate that concept. If a civilization develops technology far beyond our current understanding, it's conceivable they could create incredibly realistic simulations, potentially hosting countless iterations of life, much like our own. Philosophers have argued that if we reach a point where creating such simulations becomes feasible, it's statistically likely that we're living in one. If civilizations frequently run simulations, the number of simulated beings could vastly surpass those of original beings. Thus, it might become nearly impossible to ascertain if we are real or part of a simulation. Yet, pondering the universe as a simulation also raises significant questions about the nature of consciousness, free will, and the fundamental laws that govern our existence. If we are in a simulation, who or what is the programmer? What rules dictate this simulated reality? These inquiries not only entice us to explore the very fabric of our reality, but also lead us to reflect on the purpose of existence, whether within a simulation or outside it. Ultimately, while the idea remains speculative, it encourages a deeper exploration of both science and philosophy, inviting us to consider the limits of our understanding and the nature of the universe itself. The question of whether the universe has a purpose or is purely random has intrigued humans for centuries. At its core, the universe operates under the laws of physics, which describe how matter and energy interact. These laws govern everything from the formation of stars to the behavior of particles. This intricate system gives the impression of order, suggesting there might be a greater purpose behind our existence. However, when we delve deeper into cosmic events, we encounter random processes, such as the chaotic paths of asteroids or the unpredictable outcomes of quantum particles. These phenomena highlight the role of chance in the universe. Our understanding of the cosmos reveals a mix of structure and randomness. Natural processes, including star formation and the evolution of galaxies, can unfold seemingly without direction or goal. Philosophically, the concept of purpose can vary widely. Some individuals find meaning in human experiences, relationships, and the quest for knowledge, reflecting a purpose shaped by our perception. Others view the universe as indifferent to our existence, where life arose through specific but random events. Ultimately, the universe may combine elements of both purpose and randomness. While we navigate through a cosmos governed by recognizable laws, the existence of life and consciousness may emerge from a complex interplay of predictable mechanics and unpredictable events. In this viewpoint, meaning is not inherently built into the universe. Rather, it is created by us as we explore, wonder, and seek understanding. Our search for meaning transforms the vastness of the cosmos into a backdrop for our own stories, shaping how we connect with the universe around us. The universe presents a profound challenge to our understanding of reality in ways that continually provoke curiosity and questions. At its core, the universe is immensely vast and filled with mysteries that often defy our everyday experiences. For instance, when we look up at the night sky, the stars appear fixed in a serene backdrop. Yet, in reality, they are moving at incredible speeds and distances, many of them existing as dynamic processes rather than static points of light. One significant concept that complicates our grasp of reality is the nature of time. Traditionally, we perceive time as a linear progression from past to future, but the universe reveals that time can behave quite differently under extreme conditions, such as near a black hole. Here, time stretches and dilates, indicating that our intuitive understanding may not hold in the face of cosmic phenomena. This notion challenges our fundamental beliefs about how we experience life and how events unfold. Furthermore, the idea of multiple dimensions adds layers to our comprehension of reality. While we experience the world in 3 dimensions, theories in physics suggest the existence of additional dimensions that we cannot perceive. This implies that there might be aspects of reality that are completely outside our sensory experience, compelling us to redefine what we think of as the fabric of the universe. Moreover, quantum mechanics introduces another level of complexity. At the smallest scales, particles do not adhere to classic laws of physics and can exist in multiple states simultaneously. This phenomenon challenges the notion of a predictable, deterministic universe. Instead, we find ourselves contemplating a reality that is probabilistic and dependent on observation, suggesting that the act of measuring something can influence its state. The existence of dark matter and dark energy further complicates the picture. These elements compose a significant portion of the universe, yet remain largely mysterious and undetectable by our current technologies. Their presence shapes the structure and fate of the cosmos, reminding us that much of the universe is unseen and may operate under rules that are entirely alien to our direct experience. The universe serves as an unending source of wonder and learning, continually pushing us to question our preconceptions. It invites us to consider new frameworks and ideas about existence, time, and the very nature of reality itself, demonstrating that our understanding is an ever-evolving journey rather than a final destination. The universe is vast, complex, and often mind-boggling, leading many thinkers to wonder whether some aspects truly elude human understanding. As we delve into the fabric of reality, we encounter phenomena that challenge our perceptions of time, space, and existence itself. For instance, concepts like quantum entanglement suggest that particles can be interconnected in ways that do not align with our intuitive understanding of how things interact. This interconnectedness implies a level of complexity in the universe that can feel almost paradoxical. Additionally, the idea of multiple dimensions beyond our three-dimensional experience presents another layer of complexity. These additional dimensions may govern behaviors and dynamics that we cannot easily perceive or imagine, leading us to ponder whether our cognitive frameworks are equipped to grasp all the variables at play. Furthermore, the question of consciousness itself raises profound mysteries. What if consciousness is more than just a product of biology? This possibility stretches our understanding of identity and existence, suggesting dimensions of reality that are inherently beyond our comprehension. While we have made incredible strides through science and philosophy in uncovering the workings of the universe, the potential for truths that lie beyond our grasp remains a compelling notion. It encourages exploration and highlights the importance of humility in the face of such a vast unknown. As we continue our quest for knowledge, it is essential to embrace the idea that there may always exist realms of understanding that provoke curiosity and inspire the next generation of thinkers. The origin of life on Earth is a profound mystery that scientists continually seek to unravel. At its core, life began billions of years ago in an environment rich in essential ingredients. The building blocks for life can be understood as a combination of chemical compounds, such as water, organic molecules, and energy sources. Water is the most fundamental substance for life as we know it. It acts as a solvent, allowing different chemicals to interact and react. In the early Earth, bodies of water provided the perfect setting for these reactions to occur. Organic molecules, including amino acids and nucleotides, emerged from simpler carbon compounds through various chemical processes, likely influenced by natural phenomena such as lightning or volcanic activity. These molecules are vital because they serve as the foundational components for proteins and nucleic acids, which are crucial to the structure and function of living organisms. Energy played a key role in this process. Sunlight could have driven reactions necessary to form these organic compounds, while hydrothermal vents on the ocean floor might have provided heat and minerals that spurred chemical activity. As these ingredients came together, they formed more complex structures. The assembly of molecules into self-replicating forms marked a critical point in the journey towards life. Over time, these early life forms would evolve, adapt, and give rise to the diverse array of organisms we see today. Understanding the beginnings of life is an ongoing pursuit, constantly refined by new discoveries and theories. Each finding about the necessary ingredients further sheds light on how something as complex as life could emerge from mere chemical interactions in a dynamic environment. While carbon-based life forms are the only known examples of life on Earth, the concept of non-carbon-based life is a fascinating area of scientific exploration. Carbon is a versatile element capable of forming numerous complex molecules that are essential for biological processes. However, scientists speculate that life might exist in forms that use different chemical foundations, such as silicon. Silicon, like carbon, can form diverse structures, which raises intriguing possibilities for alternative biochemistries. Imagine a world where organisms utilize silicon in place of carbon. These life forms could thrive in environments drastically different from our own, such as extreme temperatures or high radiation levels. Instead of being composed of proteins and nucleic acids, these entities could create an entirely different suite of biochemicals that serve similar functions. In addition to silicon, other elements such as sulfur or phosphorus might also support life under certain conditions. While scientists have yet to find definitive evidence of such organisms, research continues to examine extreme environments on Earth, like hydrothermal vents or acidic lakes, as potential analogues for habitats where non-carbon-based life could arise. Ultimately, while carbon-based life is the only type we currently understand, the universe is vast and varied. The possibility of life forms with entirely different chemistries invites us to keep an open mind about what constitutes life, allowing us to explore the realms beyond our earthly experiences. Water is fundamental to the emergence of life, acting as a crucial building block in the biological process. As the most abundant compound on Earth, water provides a unique environment where chemical reactions can take place. It serves as a solvent, dissolving various substances that cells need to live, grow, and reproduce. This ability allows essential chemicals to interact more easily, facilitating the formation of complex molecules like proteins and nucleic acids, both of which are vital for life's machinery. Beyond its role as a solvent, water is also involved in maintaining temperature stability through its high heat capacity. This feature helps to create a more stable environment, which is critical during the early stages of life development. Water's liquid state is particularly important because it allows a wide range of temperature conditions, giving rise to a variety of habitats, from deep oceans to damp soils. Moreover, water participates in biochemical reactions such as photosynthesis, which is central to energy conversion processes for many organisms. In these reactions, water molecules are split, releasing oxygen as a byproduct, an essential component for the development of aerobic life forms. Lastly, the unique property of water to expand when it freezes forms ice that floats, creating an insulating layer on bodies of water. This insulation prevents aquatic environments from completely freezing over, allowing life to persist beneath the surface in harsh conditions. Water is not just a mere ingredient, it is the medium through which life formed and evolved, making it indispensable for the complex chemistry necessary for life as we know it. The quest for alien life is essentially an exploration of whether we are alone in the universe. Traditionally, scientists have focused on places that resemble Earth, such as planets in the Goldilocks zone, where conditions might be just right for life as we know it. These are often rocky planets at just the right distance from their stars, allowing for the presence of liquid water, a crucial ingredient for life. However, this approach may be too narrow. Life on Earth thrives in some of the most extreme environments, from the deep ocean floor near hydrothermal vents to acidic lakes and icy tundras, revealing that life can adapt to conditions previously thought inhospitable. Therefore, searching in places with extreme conditions on other planets and moons, such as the icy surface of Europa or the sulfuric atmosphere of Venus, might be just as fruitful. Moreover, beyond physical environments, we often look for familiar biosignatures, like oxygen or methane, that we associate with Earth-like life. Yet, life on other worlds may employ entirely different biochemistries. We could be overlooking alien life forms that don't depend on oxygen or water in the same way we do. This calls for a broader definition of what signs of life might look like, potentially expanding our search beyond traditional scopes. As technology improves, we now have tools that allow us to examine distant exoplanets and their atmospheres more closely. Observations should extend to environments we haven't considered, including moons, asteroids, and even artificial worlds. By expanding our search criteria and being open to the idea that life can thrive under far different conditions than those found on Earth, we may uncover signs of life where we least expect them. Therefore, rather than searching only where we think life should exist, we must also explore where it might surprise us, altering the very foundation of what we define as a habitable location. The discovery of extraterrestrial life would be one of the most profound milestones in human history, reshaping our understanding of existence and our place in the universe. Initially, the sheer excitement would likely resonate globally as people grapple with the reality that we are not alone. This acknowledgement would challenge long-held beliefs and philosophies regarding life, spirituality, and humanity's uniqueness. From a scientific perspective, the implications would be vast. It could ignite a wave of research and exploration as scientists strive to understand the biological makeup and environmental conditions of this newfound life. Such findings could reveal different evolutionary paths, providing insights into how life adapts and thrives in varied conditions, potentially leading to developments in biotechnology or ecology. Moreover, the implications would stretch beyond just science. The legal and ethical considerations regarding how we interact with extraterrestrial life would demand serious attention. Questions would arise about our responsibility towards these entities, their rights, and the potential consequences of any contact or interference. Just as the age of exploration brought consequences through cultural exchanges and conflicts on Earth, the prospect of interacting with alien life could provoke similar challenges on an interstellar scale. On a socio-cultural level, the revelation would likely foster both unity and division among humanity. While some might embrace the concept of a shared existence in a broader cosmic community, others may react with fear or skepticism. This duality might lead to new philosophical dialogues and a re-examination of humanity's narratives concerning life and existence. Overall, finding extraterrestrial life would not merely be an astronomical discovery. It would be a catalyst that ignites a multifaceted examination of everything from scientific inquiry to existential philosophy, forever altering the course of human thought and progress.